Good evening, everyone. I hope you can hear me and see me as well. Martina, can you please confirm that?
Yes, sir, and we can see you and hear you.
Okay, great. Thanks, Sri. Good evening, everyone. Welcome to the Robert Bosch Center for Data Science and Artificial Intelligence 11th workshop on recent progress in data science and AI. So this workshop will be a spotlight on premier papers. So where we'll have 7 exciting talks by 6 speakers on papers presented in top tier conferences last year from RBCDSAI. And so we have, as I said, we have 6 speakers, and there are going to be 7 talks, and this is going to go from 5 p.m. till 9 p.m. today. And we have a host of speakers, and we'll go over each of these talks from now. And the first talk is going to be by Vishnu Veerathu, who is with Cohesity Inc. And he's going to talk about the structure of parameterized tournaments with applications to ranking from pairwise comparisons. Over to you, Vishnu.
Thanks. Let me just share my screen. You guys can see my screen, right?
Yes.
So today I'll be presenting on the structure of parametric tournaments with application to ranking from pairwise comparisons. This was the accumulation of around 1 year of work with Professor Arun Rajkumar. So the agenda for this talk is, initially I'll be starting off with what the existing approaches and the problem motivation are. Then we will be looking at what exactly low rank tournaments and the ranking algorithms, what already exists. Then we will move on to the general structure of rank 2 tournaments and their properties. This is some novel ideas that we had and were able to prove formally. and a ranking algorithm specifically made for this, known as the rank-to-rank algorithm. Then we will be moving on to higher rank tournaments and the local global preference model and the ranking algorithm for that, known as the block rank-to-rank algorithm. Then we will be applying that to actual real-world pairwise comparison data, the algorithm for that, and its applicability in general, like how many data sets actually follow this model and such. We'll be signing off with extensions, conjectures, and other interesting open questions that we were able to formulate. So, starting with the introduction. So, the main question is, why do we need to why pairwise comparisons? So the first reason is it's simply easier to obtain pairwise comparisons, get users to give that kind of information, rather than asking users to give an ordered list of preferences. So oftentimes, if you just ask to compare item A and item B, it'll be easy to choose. Even users give more accurate data information as compared to asking them to give an entire ranking of their favorite books, magazines, etc. This can also be used in sports for sports data sets, which is primarily what we use in our work. So in sports such as tennis, you often see that tournaments are just played as a single elimination tournament. So there's no round robin stage where you have comparisons between every two players, especially when one player is very highly ranked and the other player is not. Same applies to some esports where teams are constantly changing. So it's very unlikely that you have comparisons between all existing teams. So the question here is, how do we process all available data and then rank the items, create a single ranking of all the items? So now for a bit of formalism. So the preference matrix it shows it allows us to model the comparison between any two items that are going to be compared. So Pij, this being the matrix P itself, represents the probability of an item J being compared favorably to item I. So our goal is, given a matrix like this, we want to come up with a ranking. So a ranking is nothing but a permutation, and the way we evaluate a ranking is shown in this expression here. So this basically says that this expression evaluates to the number of pairs I and J such that I is ranked higher than J, but I would lose is less favored as compared to J. So the higher the error is, the worse the ranking is. Moving on to the problem variants. So there are two main problem variants that we consider. One is the minimum feedback arc set on tournaments problem. So here we consider that the full preference matrix is present. Like for every I and J, we have a comparison other than items with itself, since that's impossible to obtain. And we consider that to be 0.5. So given the entire preference matrix, we have to come with a rank. In the second variant, we are only given part of the preference matrix. So as you can see here, comparisons between item 4 and item 2 are unavailable, and same thing with item 4 and item 3. So, and the other variant is even the known values, say this 0.3 as a comparison between item 2 and item 1, may just be approximated from available data. Say like if player 2 and player 1 played 10 games, player 2 won 3 games and player 1 won 7. So we assume this value is 0.3 and then try to get a ranking from here. So we now move on to the Bradley-Terry-Luce model. This is an existing model which is very popular, and lots of models try to approximate the parameters used in this over here. So what happens here is the degrees of freedom of the matrix is restricted from n to just nc2. The restriction helps in dealing with incomplete data, since if you assume that there are a lesser number of underlying parameters which you can just estimate, then you can actually reconstruct the matrix using the existing data. So the primary assumption here is that for each item there exists a score, a Wi, such that the comparison between two arms, say like I and j, is given by Pij equal to Wj by Wi plus Wj. So basically, the higher the score W for an arm, the more likely it is to win against any other given arm. So along this line of thought, there's a lot of ranking procedures and algorithms which try to assign a score to each arm and then just sort the items according to this score and create a ranking. So two such approaches are the first one being the board account. So this one was proposed in 1433 by Nicolas of Cusa, but then it was named by a French mathematician who devised the method independently in the 1770s. So the score of each arm is simply the sum of probabilities of winning against all other arms. So it's basically the probability of winning against an opponent chosen at random, uniformly from all other opponents. The second method, which is more widely used, is called Copeland's method, which was described in the 1950s. So this one just uses the number of wins against all other arms as the score for each arm. So the term win here describes the probability of winning against that particular arm to be greater than 0.5. So it's binary in nature. So one advantage of this as compared to the Boda method is it does not use the magnitude of comparison between two arms. So as we saw earlier in the ranking definition, how we were evaluating it, there also we were not looking at the magnitude. So this follows that in that sense. However, the con is that ties are very likely, since it's very likely that two arms are present which have the same number of wins when compared to all other arms. We do still need a tie-breaking method. So tie-breaking methods for this would include reverting back to the board account or creating a sub-tournament among those tied arms and again using the Copeland method and so on. So both of these methods require an entire preference matrix to be known, because obviously if one item has more entries populated when compared to other arms, the scores would be higher and it would just get ranked higher simply because more data is available. One solution to this problem was given by the rank centrality algorithm in 2015. So here what happens is we have an initial preference matrix as shown here. This is the same one as earlier. And some comparisons will may be missing. So what we do is we convert the preference matrix to a Markov chain. So from P to Q, where Q represents the Markov chain. And then we find the stationary distribution of the Markov chain. Then the items are ranked according to the weights given in the stationary distribution. So arm 2 gets the first rank, arm 4 gets second, and so on. So the advantage of this is it works very well for a wide range of data sets. Experimentally, it's shown to be quite versatile. And the other advantage is it does not require any matrix completion algorithm to run beforehand. The fact that data is not present is built into the algorithm already. So coming to low rank under transformations, what exactly we mean by this? So when a transformation is applied to a preference matrix, we assume it has a low rank. So one example we can take is the logit function x on x, which is basically log x by 1 minus x. So this particularly is used since when this transformation is applied on a preference matrix which follows the BTL model from earlier, it becomes rank 2 under this transformation. So since the rank is just 2, it becomes very easy to reconstruct the matrix and obtain a full preference matrix. However, when we apply this transformation to a BTL preference matrix, this does not cover all rank 2 matrices. For example, when P belongs to PBTL, the logit function, the preference matrix comes out to be XE transpose minus EX transpose, where E is the all ones vector. So each entry of this matrix would look something like an entry IJ would look like XI minus XJ. So in this paper, we examine a more general case where the expression would be given by XY transpose minus YX transpose. So each item would have two parameters now, an XI and a YI. And the relationship between any two arms would be given by XI YJ minus XJ YI. One important thing to note here is that we do primarily use the logit function, the log x by 1 minus x expression to describe our results in the paper. But we don't need it to be the logit function. In fact, there are many link functions which will serve this purpose. So the link functions, the conditions on the link functions that will follow our theoretical results are shown here. So we basically need the link function when applied on 0.5, say if two arms have equal probability of winning against each other, then it should be evaluated to a 0. And then anything which has a lower than 0.5 probability of winning should be evaluated to a value less than 0 and vice versa. So as long as the reason that these conditions are used is that if such link functions are used, the tournament does not change in structure. So in the preference matrix, we considered that 0.5 is a draw, less than 0.5 is a victory for, if you're considering arm I and arm J, a victory for arm J. And then if it's greater than 0.5, a victory for arm I. So if we apply link functions which follow these three criteria, we can simply say that consider the modified matrix and say that if the value is less than 0, it's a victory for arm J. If it's greater than 0, it's a victory for arm I. And if it actually evaluates to 0, then it's a draw. And So the choice of link function does matter when extrapolating missing information from available data. So during the extrapolation process, we do transform the existing data using this link function. So there it does make a difference. But once we have the entire tournament, like the reconstructed tournament, it plays no further part in how we obtain the ranking itself. So moving on from algebraic to geometric constraints. So the algebraic constraints we were talking about were have to do with the rank of the preference matrix under certain transformations and so on. So this takes on a more graph theory approach to the problem. So we were able to prove that the following subtournaments are forbidden under the logit function with the rank 2. When the preference matrix is rank 2 under the logit function. So here we have a basic 3 cycle and then one item losing to all 3, and the same scenario with the 3 cycle with the one item beating all 3. So coming to why this is, based on what we saw before, the fact that the preference matrix can be expressed as XY transpose minus YX transpose. The relationship between any two arms, I and J, is dependent only on the value XI YJ minus XJ YI. So if this is 0, it's a draw. If it is less than 0, that means I is preferred over J. And if it is, if it is greater than 0, that means I is preferred over J. And if it is less than 0, J is preferred over I. So the reason we have this visual representation on the right is this is reminiscent of a cross product in some sense. So if each item I can be represented by Xi Yi, say Xi Yi is one of these blue vectors, and Xj Yj is one of these red vectors, we can just say that we can easily say that the I will beat J, since the cross product due to it being less than 180 degrees counterclockwise will be positive. So the reason that we were able to say that those two, some intuition behind why those two forbidden configurations are as is, if we consider the first item to be a blue vector, going back to the previous slide for a second. So we have 3 items in a cycle, and then one item which beats all 3 of them. So if we try to see how that can happen here, so one item would have to be this, like without loss of generality, we consider it to be a blue vector. Now, so to construct the rest of the cycle, we can assume that the other one is, say, the green, one of the green vectors, and the third one is one of the purple vectors. So we can see that this forms a cycle. And then there is no arm which can beat all 3 of these that exists in the 2D plane. So that's why we are able to say that it's forbidden. That was the intuition behind it. And then we were able to prove it formally as well. So now coming to what we, a bit more of the structure. So what exactly we mean by separator over here. So we found out that in case there are a set of arms present like this, these 2 blue vectors can be grouped together, since between these 2 arms, there's no other vector has a different relationship with either one of the arms. Say if one of all 3 of the red vectors moves to all of the blue vectors, all the green vectors lose to the blue vectors, all the purple ones beat both of the blue ones, etc. So we are able to group together these vectors like this, so that the ranking procedure becomes very simple. So a representation of that is given on the right. So now we are coming to the rank-to-rank algorithm. So this basically is a ranking procedure for the model we saw earlier. So given that the cyclic nature of what we saw, we essentially rely on finding a cycle ABC if it exists. The topological, the acyclic case can be discarded by just doing a topological sort. So once we find a capital A, B, and C, we know that the ranking, we know that the items between A and B, between B and C, and between C and A are transitive in nature. So here, if we consider the blue arm to be A, the green arm to be B, and the purple arm to be C, we can say that everything in between these 2 arms is simply transitive in nature. So based on this, we have a recursive call to the rank-to-rank algorithm itself. So this is done from practical considerations, since our model may not be always followed. If in case the model is exactly followed, we don't even need the rank-to-rank recursive call. We can just say that the created subsets are going to be transitive in nature, and we're just going to go ahead with that. So based on this, we created a local global preference model where the relationship between arms in a single block, I'll come to what a block means in a second. So the relationship between arms in a single block is follows a rank 2 model, where cycles are allowed with certain restrictions and so on. And yet there exist multiple blocks, and the blocks have a transitive relationship amongst themselves. So each block is highlighted in orange. So we can see that the blocks themselves have a transitive relationship, and within each block there exists rank 2 formations. The same is represented mathematically here on the right. So despite each block having a rank 2 structure, the rank of the entire thing became rank 4 due to the global nature of the transitive, due to the transitiveness between the blocks themselves. So we devised a block rank-to-rank algorithm as well. So this one, this algorithm basically relies on finding cycles. It's similar to the rank-to-rank algorithm. We find a cycle ABC, and then we find all arms which are going to be in the same block as A, B, and C. We can say that any item which beats A, B, and C, given by S plus, will not be in the same block. It will be in a block which is above this in the transitive block structure. And any item which loses to all 3 will be in a block which is below this. So based on this, we can divide it into 3 sets: S plus, S minus, and S. And then we apply the block rank to rank, rank to rank, and block rank to rank algorithms recursively on each one of these subsets. So the correctness of this algorithm comes from the correctness of the rank-to-rank algorithm and the assuming that the block structure is correctly recovered. So this works very well when we are able to recover the entire structure, but this algorithm does not take care of actually using pairwise comparison data and creating a ranking from it. So for that, we have the pairwise block rank algorithm. So this utilizes the block rank-to-rank algorithm in the final step. But this basically gives us a procedure to create the full matrix for the block rank-to-rank algorithm to be applied. So from our input here would look more like IK, JK, YK, where IK and JK are items, and then YK is the result between them. So either a 0 or a 1. And then the comparisons, since K goes from 1 to n, there are m points in this data set, and IK and JK can repeat. So there can be like 1, 2, 0, 1, 2, 1, so that it's a 50-50 chance of each one winning. So from that, we consider a preference matrix. We go on to apply the matrix completion algorithm, and we do have to give a rank here, unfortunately. The rank can be considered to be a hyperparameter, where we try to reconstruct with various ranks on a certain subset of the data and then try to find the best rank for applying this subroutine. And then we apply the block rank-to-rank algorithm at the end. So we have some guarantees on the pairwise block rank-to-rank algorithm. So as I mentioned before, the block rank-to-rank part of it relies on the matrix structure being recovered successfully. So here we try to give a guarantee that on the recovery of the block structure itself, like with what probability does the entire structure get recovered, so that we can have an accurate ranking and have optimal guarantees for the block rank-to-rank algorithm. So we are given that if m, which is the number of comparisons that we have, total number of comparisons, is of the order nb log n, where b is the number of blocks, and k, which is the minimum number of comparisons we have between each of those between any two arms which we actually have data for, is of the form b log n by epsilon delta square. Then we have a high recovery guarantee, 1 minus 2 by nq, where n is the number of entries in the matrix. So with this essentially guarantees that with sufficient number of with sufficient data, we recover the entire structure and our algorithms will work. So we now come to the applicability of the proposed models themselves. So we can see here that a few tournaments, these were taken from www.preferencelibrary.com. So these all are tournaments which follow the block structure quite well, and they would not have followed any other model. Like the BTL model does not allow for cycles. So all these are examples of where our model comes in handy. And on the right side, we can see the fraction of tournaments which our model can successfully model over previous models. Say all this in blue is what previous models can model, and our model can do it as well. In the green is where we have a significant difference, since we can model all these like ice skating preference tournament, sushi preference tournament, election candidates preference tournament, etc. And the part in red is something that even our model cannot model. It is simply too complex for our rank 2 block structure. So some of the extensions that we had is that since we now found out the structural guarantees for the rank 2 case, we now want to see what happens in the rank 4 case. So we have a belief that our what we're looking for has to do with doubly ranked poles. So a doubly ranked tournament is simply a tournament in which the number of wins of each arm I and j is the same, like the total number of other arms that they defeat. And for each I and j, that ti plus intersection tj plus is a constant k. So the number of arms that both I and j defeat together, both of them at the same time, is a fixed constant for all I not equal to j. So that is a doubly regular tournament. So when we say cone, we just imply the presence of one additional item, which is preferred to all other items. So the forbidden configuration for the rank 2 case was a 3 doubly regular cone. We have been able to prove that 11 doubly regular cone is forbidden in the rank 4 case. And there also exists a size 10 tournament that we have here that is forbidden in the rank 4 case as well. However, our conjecture is that a rank 2D tournament forbids 4D minus 1 doubly regular cone. So for the rank 4 case, we ideally would get some results saying that 7 doubly regular cone was an impossible configuration. However, it is unlikely that we'll be able to prove this statement alone, since this further implies the Hadamard conjecture that such cones exist for all positive D to begin with. So it's not known that such cones exist for all D. The 7 does exist, so that is something that we can aim for, however. So some open questions that we had which seemed interesting were that an optimal polynomial time rank 2 for ranking algorithm for the rank 2 case is now known. So can we create similar ones for rank 4 and higher cases? So obviously for rank n, it is an NP-hard problem. So the answer is simply a no. So does one exist for rank 4? And so up to which rank can we possibly expect such ranking algorithms to exist? Also, is there an efficient way to find out whether a tournament is representable for a given dimension? The results that I showed on the previous page took a lot of filtering and like brute force computing to create that these are actually forbidden and cannot be represented with that with rank 4. And if it's not rank 4, if it was rank 6, it would be far more complex and much more difficult to create such a tournament. The last one was, is there a exhaustive finite set of forbidden subtournaments for each rank-based restriction? So in the rank 2 case, using those two size 4 tournaments, we were able to say that if a tournament does not include this as a subtournament, it does follow the rank 2 case. So are such configurations obtainable for higher rank tournaments, or is the set of sub-tournaments just infinite? Like even if we have a set of tournaments, there may be some other tournament which does not have any of these sub-tournaments, but still cannot be represented with a given rank. Thank you, and acknowledgements. Some of the later work that we did, especially in the extensions and conjecture section, is currently under review, and with one of Professor Arun Rajkumar's students, Abdul, and I and Arun Rajkumar are co-authors for that. That's it from me.
Thanks, Vishnu, for the talk. So in the interest of time, if there are any questions, you can take them in the Q&A box. Please type them in the Q&A box. We can perhaps move to the next talk now. Thanks, Vishnu. By the way, this paper is going to be presented at NeurIPS 2021. So our next talk is going to be by Dev Yashpal Sheth, and this is going to be on unsupervised deep video denoising, and this is a paper that will be presented at the International Conference on Computer Vision this year. Dev, over to you.
Thank you, sir. Is my voice clear and is my screen visible?
Yes.
Yeah. Hey everyone, I'm Dev, and I'm going to present the work on unsupervised deep video denoising. So it was a joint effort by a lot of people, as you can see over here, and the basic problem is as follows, right? So there are a bunch of folks who have access to transmission electron microscopy data for catalytic nanoparticles, and they take these images for of these nanoparticles, right? And they're not really clear because if you increase the exposure time for the image, it costs a lot, and if you decrease the exposure time, it's a lot noisy. So it looks something like over here, and that's not really helpful. We want to know the structure of the underlying data at hand, right? And then that's where deep learning comes to our rescue, and we'll see how. So this was actually a collaboration between folks at ITM, NYU, and ASU. From ITM, it was primarily me and Professor Mitesh Thapra. At NYU, it was Shreyas and Professor Carlos Shanero. And the ASU folks were Joshua Raman and Professor Peter. So I'll just move on. Yep. So our goal is video denoising. So we had this videos of catalytic nanoparticles, but to begin with, to model the problem, let's see how we can model the natural videos, right? So let's say we have a bunch of frames from a video. We want to learn some function, which I'll explain what this is in some time. And we want to come up with a clean frame at a particular timestamp, right? So let's say you're given a frame window of 5 frames from t-2, t-1, t+1, and t+2. You have these noisy frames. And now you want to predict the clean frame at time t using the following context, right? So state of the art in this particular domain right now is given by supervised denoising, where what you basically do is take a noisy frame and take its corresponding clean frame and just ask a neural network to learn this function, right? So you have the noisy frame as input, the clean frame as output. Just simply fit an L2 norm between the learn function and the clean frame, and that should be enough. That's what the supervised state of the art does currently. But there's a problem with this. And the problem is that this requires access to clean videos. So the case that I described to you before, it really does not have access. We really do not have access to clean videos over there. So there are a bunch of cases where clean videos are really difficult to acquire. And the first case is raw videos, where whenever you capture a video using a normal camera, it actually gets converted to the raw format, and that raw format in itself is also quite noisy. There's also fluorescence microscopy, where there are a lot of noisy videos which are captured, and there's a need to denoise these videos, and the electron microscopy application that I just motivated. So to deal with all of this, we introduced unsupervised deep video denoising to get rid of the requirement of the clean videos altogether. But to do that, we need a series of ideas, which we'll go over now. So the first one is noise to noise. Let's just call this cool idea 1. So the idea over here is this, right? If you take a noisy frame and model a network to learn another noisy frame, which is a different noise realization of the same underlying frame. So you have this frame, say X, and now after the y, noise over it, say X plus N, it becomes Y. And then over here, you have another noise realization over the same noisy frame, X plus N dash, that goes to Y dash. So now just learn a function from Y to Y dash. In doing so, if your noise is zero mean, which is generally the case, so generally over here, the noise is Gaussian or Poisson, and in both of the cases, they are zero mean. And if the noise is zero mean, the network over a large data set will just learn to model the function X, right? It'll learn to model the clean frame, because that is what is going to minimize for over all the noise realization, over all the noise realizations. So that is one way to look at the problem and to get rid of the clean frames, right? So instead of modeling, instead of going to set the target as clean frames, set the target as another noise realization. But this also has a problem, right? So now if you want to do this, and if you want to apply it to say some downstream applications, again, you have to capture the same video twice, right? And to create the same circumstances such that the same kind of things happen in the same in the two videos that you capture, for you to have two different noise realizations is a bit tricky. So then there's a cool idea 2, which is noise to void. So over here, what you do is, because we are dealing with neural networks in all cases, or let's say CNNs. So if you're, let's say, denoising this particular patch in this noisy image, then if you somehow restrict your network to not look at this particular pixel and look at only the surroundings of this pixel, and now model your network to predict this particular pixel, then it will prevent it from learning the identity. And now you can train on this same image, right? So you can feed in the network the noise Y, and then your network will be f of, the network output will be f of Y, where f is some function that you want to learn. And now just fit the loss function f of Y minus Y. So ideally, if you didn't have this particular mask over here, that would lead to just identity function. and it would not really learn anything. But if you have that particular mask, and if you're not using that particular value in that from that pixel, then you are ideally learning noise to noise, but on the same, you're doing noise to noise, or essentially you're doing denoising, but you're not learning the identity function, right? So you're using the surroundings of a particular pixel to predict the true value at that particular pixel. But this thing is costly, right? Because every time you do a forward pass in the network, you'll have to mask some pixels out and then mask them from the loss function as well. Now we cannot mask out the entire image because that doesn't make sense. So you'll have to mask only a fraction of the image, and then your training time goes high, right? So to avoid this, again, there's a cool idea 3, which is blind spot network. So now instead of doing masking, which is costly, we design an architecture which essentially does the blind spot thing for us, right? So let's say you have an image. What you do is, let's say you're using units to model your denoising function, and to denoise, just shift your image downwards, in the sense that if you are looking at the entire image, instead of that, just look at the top half of the image and then pass it to the network. So that becomes the first part of the unit. So now before each convolution, because you're shifting your image downwards, the pixel that you're predicting, which is, let's say, the center of the image as of now, goes out of your window. But there's also one more problem, which is that now you're only modeling the top half of the image. So to get all the parts of the image, you can parallelly model 4 different networks, right? So you can use the same network, but you can do 4 forward passes in which you'll first learn the top half of the image, then you'll rotate it by 90, then you'll learn this half of the image, then you'll again rotate by 90, and you'll learn the lower half, and then again rotate by 90, which is this one, and then you'll get the right half of the image. So now you have parameterizations over all 4 halves, which are extending in all 4 directions of your particular pixels. And then you have learned a function over all of them. Just combine them using 1x1 convolutions. And then this particular image over here has seen all the pixels in its surroundings except the pixel itself. So this is a neat way to model the blind spot in the network in order to do noise to void. So that's one thing. But up till now, if you notice, we have only been dealing with one image to one image, right? So we are going from one frame to one frame. Now, because we have a video, we have access to more information as well. We have frames, and more or less the frames which are nearby to each other have some information about the particular pixels in that middle frame, right? So if you have a frame at t, the frame at t plus 1, if you are able to model the motion compensation between these 2 frames, you'll be able to utilize information in t plus 1 to denoise at t. So how do we effectively model this frames, right? So a nice idea which was given by FastGPTNet is that input 5 frames at once and have 2 denoising blocks. The first denoising block deals with 3 consecutive frames at once, and it produces some output. That output is again concatenated and passed on to another denoising block, and that particular block gives you the output at frame t, right? So you'll pass a context window of 5 frames from t minus 2 to t plus 2, and you have denoising block 1, denoising block 2, and then the output will be at output frame 3. And this is the current supervised state-of-the-art network to do denoising. We just want to adapt it to the unsupervised domain, right? So now our core idea is simple. So we have a context of 5 frames, and we want to predict this pixel in the red dot over here. And we want to utilize information in all of these shaded regions by different forward passes. We essentially use the same network, but it's different forward passes because you'll do a forward pass 4 times. And your field of view over 5 frames to predict this particular pixel is going to be this, right? Anything which is shaded over the image is going to be available to you as context to denoise this particular pixel. And yes, estimate a pixel using the noisy pixels in its spatio-temporal neighborhood, and you should be able to denoise well. It uses all the core ideas, cool ideas that we introduced before this. So now our final network architecture looks something like this, right? You have 5 frames. You'll first do a rotate function, and you'll pass all of these frames through rotates, and you'll rotate them by 0, 90, 180, and 270, and you have 4 different channels for all of these. And once you have that, you have an architecture which is cascaded in the form of D1 and D2, which is denoiser 1 and denoiser 2. And then you have some outputs from all of these 4 architectures, unrotate them, pass them to 1x1 convolutions, and then now fit a model based on this, right? So now you're again predicting the same frame again back to this. So your target over here is just the frame T. But because it's a blind spot, you are not using the pixel value at that point. You'll be able to denoise that particular image. Again, the field of view is again represented over here, and the network color matches the masks over here, right? So the blue network corresponds to the field of view, which is shaded in the blue region because it's upright. If you rotate it by 90 degree, you get the pink network, which is dealing with it. So it's the same network, but it's different forward pass, right? So you get the pink version of it, and then that particular mask is going to look at this particular frame, right? So that's the idea. And if we do this, our network, which is called UDVD, achieves the same performance as the other state-of-the-art methods, right? So if you have this particular clean frame, for now we are dealing with natural videos. We'll move on to different domains as the talk gradually progresses. And if you corrupt it with Gaussian noise with mean 0 and sigma equals to 30, this clean image is going to look something very hideous like this. And now if you use the supervised state-of-the-art for this, on this, it'll give you something like 37.73 PSNR. The higher this metric, the better the performance. For a clean frame, PSNR is generally infinite. And it's peak signal to noise ratio, right? There are unsupervised methods out there, apart from what we introduced, but they're not really truly unsupervised. We'll come to that in the later part of the talk. But even considering those, our network gives the current state-of-the-art results, and they more or less match what the supervised state-of-the-art provides, right? I'll briefly also show you some examples of our denoising methods. So over here, the top half represents the noisy input to the network, and the output of the network is the bottom half. You can see that it denoises quite well. Similarly, it goes for other videos as well. So to put it in terms of raw numbers, we tested it out on 2 standard video datasets, the Davis and the SET8 dataset. And we compared it with a bunch of methods, right? There are traditional denoising methods based on supervised CNNs and unsupervised CNNs, which is us. And we see that we are nearly the state of the art on all of these fronts, right? So because we are using a context of 5 frames, we also do an ablation study in the sense that we only use a single frame denoiser, which is just an image denoiser of our own network. And we also just test out the 3 frame version, which is just denoiser 1. So if you remember in our architecture, we had D1 and D2. If you just take D1 and denoise just 3 frames, which is the, let's say, context of 3 frames and denoise the middle frame, we also do that ablation study. We don't go beyond this to 7 frames or more than that, because that is computationally not cost effective. So we stick to 5 frames for now. And the supervised state of the art, as I said, is given by fast AVDNet or DVDNet. And our numbers are quite close, and even better if you look at the other test set. So Davis has a train well test component, and we trained on the train component of Davis. And then we tested it out on Davis, and naturally over there, our numbers are good. But SET8 is a different distribution. It's not a different distribution in terms of the domain, but the videos are generally fast moving, or something like GoPro videos, which I showed over here, right? So over there, the performance drops off, but we are able to generalize better than the supervised CNN networks. But over here, there is still a problem, which is that in many practical situations like microscopy or something which we motivated from, right, there is very limited noisy data available, and we are not able to learn, right? So over here, we still had, let's say, 30 or 40 odd videos over which we could train our networks. But if you go to scarcer domains, over there, you're not able to collect clean frames. That is one issue, but you're not even able to collect more noisy frames. So you'll have just, let's say, 40 frames from catalytic nanoparticles, and those are the only 40 frames that you'll ever deal with. And you have to denoise based on just looking at just 40 frames. So effectively, you just have one video available from one of these data sets, and that is all you get to train, test, well, whatever. So what do we do for such cases, right? So to denoise single short noisy video sequences, like exclusively single videos, where you're only given a single noisy video sequence, and you have to denoise based just on that, right? You don't have any auxiliary data available. So we introduce a bunch of aggressive data augmentation techniques. So the first one, it's a standard thing, but what we do is we keep out the last 5 frames of each video. We separate it out and we train on the first 25 frames or the first 30 frames or whatever is the available. So over here, if we have a video which is 75 frame long, then we'll use the last 5 frames for early stopping and the first 70 frames to train our network. So it's just to early stop based on the val set which was created by the last 5 frames, and then we just train on that particular video and we test it out on the same, right? So other methods like fast DVDNet or even our version of UDVD, which I introduced before, was trained on an entire data set of videos. Over there we had val set. Our validation set based on which we did stopping was different from our training set, but over here your training, your testing, and your validation all has to come from the same video. So we use the first 70 frames to train, the last 5 frames to validate, and the entire network is just tested on that particular 75 frames, right? And we introduced 2 augmentation techniques, which is flips. So you can naturally flip the videos. It is a standard augmentation in Vision. And we also do time reversals where you can play the video backwards as well to train, right? That's not going to affect you in any way. And if you do that, what we notice is that even by training on just one single video for a whole network, we achieve the performance of something which is trained on an entire data set, right? So MF2F is another unsupervised technique, which is not really supervised in the sense that it uses the fast DVDNet architecture, which is pre-trained and then just fine tunes over a noisy video, which is not applicable, which is not really adaptable, let's say, to microscopy domains. Because if you use a backbone which is pre-trained on natural videos and you apply it to microscopy, it will not work, as I'll show later. But our framework is trained from scratch on just one single video, and we are able to achieve state-of-the-art performance based on this stack, right? So we also show results for a variety of noise levels. So over here, I have shown a table for sigma equals to 30, which is Gaussian noise with mean 0 sigma 30. And I've shown results for each individual video over here, right? So all of these columns over here that you see are videos, and the table is populated with PSNR values. And this is just a mean of all of these videos, PSNR values, right? So moving on, we did the evaluation on the entire data set as well, in the sense that we took the 30 videos from the Davis test set and trained a network each on each of these videos and then calculated numbers. And then we again see that we are matching the performance that we are able to do when we are able to train on the entire data set, or even if we train on each video separately, we are able to match the performance. And we do it across noise levels, right? So if you do it on sigma 30, we'll match the state of the art. If you do it on sigma 90, we'll beat the state of the art. So because all of these networks were trained on low noise levels, they weren't really tested on high noise levels. And now because we have the capability of training on high noise videos directly, we do that and we show that we are able to achieve large gains in performance. So UDVD combined with aggressive data augmentations, flips and time reversals, trained on a single noisy video from scratch gives the state-of-the-art performance. And to show the real life application over here, right? So we had this particular image as the motivated example, right? So we have this noisy input, and the UDVD-S, which is trained on just a single video, gives this particular output, which is more or less revealing the entire structure that we want to really know of the underlying nanoparticles, right? And I mentioned that MF2F, which is another unsupervised method, uses a pre-trained fast DVDNet backbone, right? That doesn't really work out over here because it was pre-trained on natural videos and then it's fine-tuned on microscopy videos, so naturally it will fall out. So this in essence tells you why you need something which you can train from scratch and which you can directly go and apply. We also tested out on raw videos. So for raw videos, it's easy to get clean videos, unlike the microscopy domain. And over here, there are a lot of data sets available. There are also a lot of supervised techniques with DNOs over there. And we are able to, again, beat the state of the art in that as well. So primarily, we deal with 4 types of videos. We have 2 videos from fluorescence microscopy and a bunch of raw videos and the electron microscopy videos. And over here, you see some DNOs frames of all of them. Yeah, this is just some examples again. So if you notice, there is a light blurring over here in the fluorescence microscopy video, and it's all cleaned out once you apply UDVD. And this is, I guess, the most promising thing that you can see, that you cannot really see anything over here. But yeah, there is some structure behind all of this that is going on over here on the left. So moving on, so it's denoising, but what function does it learn, right? So it works, yes, but how? So to investigate that, we compare it, or we sort of go back to some traditional methods, right? So traditional methods generally involve linear filtering. Over there, you design specific denoising filters, which are then multiplied with the image, and then that is going to denoise particular pixels and so on. And for videos, you'll first use motion compensation to map the pixel from a frame at t to frame at t-1, and then you'll fit a loss function between these two frames and so on. So this is what the traditional way to go about this problem is. But we only learned a data-driven approach, right? We had a data-driven approach, and we just want to investigate whether our approach is doing what traditional methods are doing, right? Does our approach make sense? So if we model the denoising pixel, let's say d of I, we can write the first order Taylor decomposition for our denoise pixel in terms of the input and the denoising function f like this, right? The gradient of the network and the image itself. And because now we have 5 different frames over which we are training the network, so we can just write it as a function of all of these 5 frames. So the gradient of these networks basically can represent a filter, and it does indeed represent a filter, as we'll see later. So if you are denoising this pixel in green over here, you're basically have input as all of these 5 noisy frames, and the gradient of the network delta f of I, which is back propagated to the frames. And if you multiply all of them, then you get your denoise pixel, which is green over here. So if you visualize as filters, this is what it turns out to be, right? So let's say the clean frames at t-1, t-2, t-1, t+1, and t+2 are something like this. For sigma equals 30, your noisy frame looks something like this, and your denoised output is this. Then the filters corresponding to each of these frames are something like this. You are basically modeling the pixel which is at the middle of this cross. And this is what your filters actually look like. And these filters will try and average over larger areas as you increase the noise level as well, right? So over here you had sigma equals 30, and it was relatively easy to denoise than if you had something like sigma equals 60. And now if you have a harder problem at hand, you need more resources. So it'll go and find more regions from where it can denoise, and your filters will naturally increase in size. But you can also notice one more thing over here, right? It's that if you look at this particular pixel, which is, let's say, over here, that guy near the chest of this guy's shirt, right? In this image, it's over here, which is exactly where this red blob in the filter is. And in this particular image, it's just moved down like this, and it is also over here, right? So the network is also implicitly trying to learn motion of objects, and it's trying to denoise. So that is one thing that we discovered by visualizing the filters of this. So now if you can just average out these filters and find a point, you can basically model the motion of the object or the pixel at the center of the teeth frame from t-1 and t+1 and so on, right? So you can basically have arrows which tell you the motion of this particular pixel in t-1 frame and t+1 frame, right? So we visualize this motion as well. So if you had an input noisy frame which looks something like this, and you had a state-of-the-art algorithm which models flow between frames of a video, right? Keep in mind that the flow algorithm that we use to model the motion compensation is actually done on clean frames, not on noisy frames. And it gives arrows for pixels which are something like this. And because we are only doing gradient computations to model flows, we can do it for supervised as well as unsupervised networks. And we show that even data-driven approaches like ours and the supervised state-of-the-art approaches, internally, they are doing implicit motion compensation while denoising. And as a future direction of this work, we also want to discover this, right? So if we use the denoising objective to train networks, can we really model the optical flow in the videos as a side problem, right? So that is one thing. And it's not really exact optical flow that is calculated. As you can see, from the comparison between our flow and the state of the art, or let's say the ground truth motion compensation flow. But it's averaging over regions which are always white, right? So if this bus is moving, let's say left or right, the whole region is just going to look white in the video, right? So the denoising function just needs white regions to go and model the pixels. It doesn't really need exactly that pixel. But if it's something on the edge, or it's something which is a small region, then it'll go and exactly find that region in the next frame, and then it's basically doing motion compensation for you over there. So thank you for listening to the talk. And we have a GitHub page maintained for this particular project. You can check out our code over there as well. And you can find more information and our paper over there. If you have any questions, please let me know.
Thanks, Dave, for the great talk. We do have time for 1 or 2 quick questions. If there are any questions, the audience, you can raise your hand and I'll allow you to talk. Or you can paste it in the Q&A box, and I will request Dave to respond. Okay, maybe if you have any questions, please. Okay, so there is a raised hand, I see. Yeah, so Sania, you can go ahead.
Yes, so you have mentioned that your work is, your work is on deep video denoising, and there are some traditional baseline methods which do not involve neural systems for your task. So exactly how much do neural systems, including yours, improve over these traditional baseline methods?
Yeah, sure. I'll just flash the table we have in the paper. So over here, if you see the state-of-the-art traditional methods, we are able to get almost 2 PSNR points improvement over them, right? So VNLB and VBM4D are some of the state-of-the-art traditional denoising methods. And for the Davis test set, we observe nearly 2 dB performance improvement over sigma equals to 30 Gaussian noise. We did not really test it out against traditional methods exhaustively for different noise levels, but it was established in the supervised CNN papers that CNN was the dominant approach.
Okay, thank you.
Yep.
Thanks, Dave. In the interest of time, I'll request the others to type their questions in Q&A, and Dave can answer there.
Sure.
Thank you for the talk. Yeah, so we can move on to the next talk for the day. And that would be by Ananya Sai on perturbation checklists for evaluating natural language generation evaluation metrics. And this paper was presented, or it's going to be presented at EMNLP 2021. Over to you, Ananya.
Yeah, thank you, sir. I hope my screen is visible and that I'm audible.
You're audible, but is there a noise?
Oh. Okay, I'm actually on headphones. Should I try removing them?
No, now I think it's fine. Yeah, I think it's fine.
Okay. Cool. So, yeah, good evening, everyone. This paper that we recently presented at EMNLP 2021.
Sorry, Ananya, we can't hear you now. Is that just me? Or?
Even I cannot hear you. Can you go again, Ananya?
Oh. Hello. Yeah. Am I audible now? Sorry for this. I think there's some rain and hence the network is having some issues.
Sure, I think you are audible now. You can go ahead.
Yeah. Okay. So I was just saying that the title of our paper that we recently presented at EMNLP 2021 is Perturbation Checklists for Evaluating Energy Evaluation Metrics. So first, let us look at what is NLG, which stands for Natural Language Generation. It refers to a software process that outputs a human understandable text in one or more natural languages. So there are already several NLG models that have been proposed through the years, starting from something like rule-based systems or statistical models to the more recent RNN-based models which use deep learning. And another approaches where we have transformer networks which have some several thousands or even millions of parameters. Right? So the space is continuously evolving, but how do we know that the outputs that we get are good, right? So for that, even the evaluation metrics need to be up to the mark. First, to understand this balance, let us look at a few examples of NLG tasks. A popular example is machine translation. So, for example, if we have to translate from French to English, this is how a data set would look like. There will be several French source sentences and reference English translations. And what the model, after being trained to produce such English translations, will be evaluated on the test set by checking how similar it is to the reference translation, right? So suppose these are the outputs that were generated, which we will interchangeably refer to as hypothesis or candidate sentences. So, for example, here it actually means that grapefruit is my most loved fruit, but banana is her most. But if we have something like grapefruit is my most expensive fruit, but the banana is her most loved, here the meaning itself is changed. And though the second example has something called beloved, which sounds a little awkward, this at least retains the meaning of the original sentence as such. So the criteria that is used in popular literature is fluency and adequacy for these tasks. Similarly, if we take another task of data to text generation, which usually consists of a set of triples that are given as input, and the expected output is a natural language sentence that ties together all this information, and this can be done in several ways. And suppose there are entities such as dates, then it can be written in some other format, but then the translation has to happen correctly. So whatever is getting generated, that has to retain the correct information, such as so in the sense it has to be faithful to the original information, and it also has to be informative. That is another parameter, because some of the outputs might cover that she was born on this date and born in this place, but it might leave out that occupation. So the informativeness or the coverage becomes another criteria. Yeah, just another example is question generation, where the context would be something like an image or paragraph on which the questions are to be generated. And this is a bit more open-ended, as you can see from the previous tasks, because there could be some other question which might not have much overlap with this, but it will be, as long as it satisfies these criteria, it will be an acceptable question. And let's just look at the criteria. Fluency is a common criteria across several NLG tasks, but we also want, in case of question generation, the generated question should be answerable. So where was this photograph taken, for example, is the airport, or things like that are answerable. But if we have a more complicated question, such as which city is this, that might be a little trickier to figure out. And suppose in this case, maybe we can see the buildings and try and guess. But if it was more of a image of just a runway with an airplane, then it will be tough to say whether that is the name of the city, right? So it has to be answerable. And it also has to be relevant to the image. That's a desired criteria. So if we ask something like how many passengers can fit in a A320, that is actually maybe answerable, but not necessarily from this image. Or whatever context is given, when we have the task of question generation, we want it to be related to that particular image or paragraph or whatever is the source. The reason I'm bringing out all these criteria is because these have been used in literature to evaluate the various generations, specifically in case of human evaluations, right? Before I get there, I just want to also highlight the fact that there are several energy tasks which things like machine translation, summarization, image captioning, or even dialogue generation, but each of them have their own set of criteria that need to be satisfied. And like I mentioned, the ideal case for evaluation of these energy tasks is to employ human evaluators who will judge the generated output along these several criteria and decide whether it is a good output or not, and along which dimensions it is bad. But the one problem with having human annotators evaluate all outputs is that it's not scalable. So if we have a data set of even more than 10,000 or something like that, it becomes extremely time consuming and expensive to have humans evaluating the outputs of multiple models. And the space is also growing very fast. So it would be impractical to include this evaluations in the model's training loop, or if we want to just change a few hyperparameters and evaluate the outputs, then again, waiting for human feedback to come will be very time consuming. Which is why, what then is the practical way to evaluate these energy tasks, right? And the answer is automatic evaluation metrics. And there are already several automatic evaluation metrics out there. I'll try to give a brief overview of some of these criteria, but largely we can think of these automatic evaluation metrics as task agnostic or task specific. In the early days of all the energy models, there were a lot more task agnostic metrics, in the sense they were proposed for one task and they've been reused for almost every other energy task, irrespective of whatever criteria was required. And these can further be classified based on the technique that they use, such as whether they are dependent on words or whether they make use of embeddings and so on. Just to give you an example, I'll walk through a few of the techniques that the evaluation metrics use. So for example, the word-based metrics, they look at the reference sentence in the candidate and they look at how many n-grams match. N-grams are set of n words that appear together or consecutively. So in this case, 2 hours and the airport are 2 grams or bigrams. And metrics like BLUE compute the precision of how many mapped unigrams are there and how many mapped bigrams are there. This precision is computed per n-gram count, and then it takes the average precision across several n-grams. That is how BLUE is computed, for example. And then there are other variants of word-based metrics that we saw in this table, which use different other combinations of precision or recall, or the F1 score, which is usually computed as the harmonic mean of precision and recall, right? So the other approach with word-based metrics is to use edit distance, in the sense how many changes or edit operations are needed to go from the candidate to the reference, right? So and then we can just take the ratio of the number of edit operations to the reference length. Yeah. The other approach is to use embedding-based metrics, where first, instead of just directly comparing the surface form of the words, we convert every word into its embedding form. Already there are popular embedding techniques like word-to-wake or glove that are created in such a way that each word is each word's embedding is close to another related word's embedding, right? Like extremely and very, or rich and velvety. Yeah. And now there are several heuristics which will try to match these embeddings, or even aggregate the word embeddings of the reference sentence and the candidate sentence and take the max or average and then finally compute the cosine similarity. Right? Yeah. So the next step is to also, instead of us computing this max or average, we can have a neural network model figure out what is the best way to combine each of those embeddings. So essentially, we take in the reference and the hypothesis, and we learn the set of parameters theta that will help the y hat, sorry, this has to be y hat, to be similar to the human score provided scores of y. That covers the branch of all the task agnostic metrics. And as you can see, early on, there were a lot of word-based embeddings that were proposed in the early 2000s. But more recently, there have been a constant exploration of these various other methods, so that it will, the main aim is to have these automatic evaluation metrics correlate with human judgments. And especially in the recent times, more and more of trained or contextualized embedding based metrics have become a little popular, though Blue and others are still used by the various energy models to evaluate various energy models. Right? And apart from all these task agnostic metrics, there is also a recent move towards task specific metrics. And most of the metrics mentioned here, which are proposed to evaluate different tasks, are all trained evaluation metrics. So essentially, in the trained architecture that I showed earlier, we also have something called the context, which could be an image or a paragraph or whatever that gets encoded, and then the input X here is the whole the concatenation of all of the context and reference and candidate, for with which we learn the y hat. Yeah, this is just to give a background of set up the background for the paper. But the main point of the paper is that the human evaluation metrics or human evaluation methods ask humans to provide scores along multiple criteria apart from an overall score. But most of the automatic evaluation metrics either provide a single overall score, or they provide a classification whether they think the output generated is good or bad. Right? So this single overall score would make sense if all of these criteria were correlated. Right? So for computing the correlation of those different criteria, we gather some existing human evaluation scores along different criteria for various tasks, which are linked here. And most of these are greater than 1,000, and some of them have in-house annotators, but some have crowdsourced annotators or even expert annotators in some case. So we take this data, and for each of the tasks, 6 tasks that I mentioned earlier, we compute how well each of these are correlated. So the diagonal is missing because data coverage with data coverage would be correlation of 1. But otherwise, we have something like correctness and data coverage, or fluency and data coverage, for example, have a very low correlation. So it doesn't make sense to have both of these to be, it doesn't make sense to have a single number try to capture both of these uncorrelated criteria. And this table is dependent on the data set and the outputs of the models that were considered and so on. But overall, we can say that at least a few of the criteria have slightly distinct. Few of the criteria pairs have different low correlations, and it, for every task except the machine translation case, where popularly only adequacy and fluency have been used, but more complicated tasks like dialogue generation, where there are several criteria, except this dimension of interestingness and enjoyability, which are highly correlated. Most of the other dimensions or criteria seem to be important to get the full picture, right? And so is the case with summarization. We want fluency, consistency, and relevance to be different criteria. Yeah, the other question that we wanted to ask is whether the metrics capture any subset of these criteria that the humans are providing evaluations on. So what we do is we take all these metrics along the x-axis, and for every task we have the criteria on which we have human scores available along the y-axis, and we have computed Kendall-Tau correlations, and yeah, so we make a few observations, or the key takeaways are as follows. So we have these pre-trained or trained metrics such as BERT score, Blewett, Moore score, which despite being task agnostic metrics actually have some of the highest correlations across several tasks. Even more than the task-specific metrics such as Supert and Blank or Tiger and Wilbert score. Or in fact, for dialogue generation, we have we actually have all the metrics on the y-axis and the criteria along the x-axis. The reason for that is most of the task agnostic. We couldn't compute the task agnostic scores because of the way in which the data was present. But excluding that, we find that these pre-training or training helps metrics to be almost as good. And it also means that we should do a better job with respect to proposing task-specific metrics. Again, these task-specific metrics also provide a single score, and there are no criteria-wise scores as of yet. Right. And the overall takeaway from this is that despite all the computations that we have done, along most of these criteria, there is not much correlation that any metric achieves, except for this few numbers that are obtained on question generation. So out of the 271 correlation values that we have computed there, 228 are poor, which is less than 0.3. 35 are moderate, which means 0.3, between 0.3 and 0.5, and only something like 2 or 3 are high correlations. But apart from just knowing that these are poor correlations, can we get more fine-grained insights? In fact, this is a recurring problem with automatic metric scores, where there have been several complaints of poor interpretability. For example, what does a particular metric score mean? Say if we have a blue 17, what does it mean? And if I think a score is bad, is it due to low fluency or low adequacy, or both? And by how much should my new energy model improve on a metric score in order to be considered an improvement over older systems? So all of these are also some questions that have to be answered. In this work, we don't claim to answer these, but our main goal is to get some more fine-grained insights into the different evaluation metrics, where they do well and where they don't. So we follow this recent paper called checklist as an idea, and propose something called perturbation checklists, which are used for evaluating the evaluation metrics. And the idea is to perturb a valid reference sentence such that it gets affected on a specific criteria, and then check if a metric catches that perturbation, which we decide by checking if it appropriately changes the score. So what I mean, I'll explain with a few examples. Fluency, as I mentioned, is a criteria that is required for all tasks, and we want to see if things like whether a metric can catch a missing or misplaced punctuation mark. So we just either drop punctuation marks or change them. This, of course, wouldn't affect many sentences by a lot, which is why we also take the help of human judgments to quantify whether this is a minor change and whether they will penalize it a bit or whether they think it's a major change, something like jumbling the word order, which might cause a bigger fluency disruption, and hence humans would also annotate it to be of a higher penalty, right, or a low score. And yeah, things like subject verb disagreement or dropping some stop words or articles or even introducing typos would all affect fluency. Similarly, for each of these other criteria that were discussed before, we propose different perturbations. So informativeness gets affected if we introduce a negation or change it with antonyms, or if we drop a few informative words, not stop words, which affected fluency, but some informative words, or if we use some hyponyms. And for in case of summarization, even the flow or of the summary is important. So if we reorder the sentences, that is probably another problematic thing that, and we want to see if metrics can capture that. So a more exhaustive list of all of these perturbations is present in the paper, which you could check out. So I'll, if the idea is clear, I can move on to what we do with on top of this. So we first compute whether the score. We want to see if the score change provided by a metric is same as the score change provided by a human. So what we do is if we compute the score provided by humans on the unperturbed sentence P or the actual reference sentence P, and then also compute a metric score on that same sentence P. Then we perturb that sentence to be affected along a specific criteria C by using some template T that I discussed before. And now we compute the difference between each of these, and that is what is plotted in this diagram here. So the darker the red, it means the more is the deviation, or rather the perceived drop in quality by a human and the perceived drop in quality by the metric has a very high difference. So some insights from this are as follows. So if we take the task of machine translation, we notice that these perturbations such as adding negations or changing the numerical values or names or replacing with antonyms, they significantly alter the meaning of a sentence, and hence a human would have given them a very low score. So the change in score would be high, whereas none of the metrics drop their score adequately, which is why the overall thing ends up being a dark red or showing that the metrics don't perform very well on these. And this is true even in case of this bird score and blue earth, which which were some of the relatively best performing metrics on the yellow heat maps, where we were checking which metrics correlate well with human judgments, right? Yeah. The other problem is that task-specific nuances are not captured. So if we take the example of question generation, things like changing question words or dropping question words would affect the answerability of a question. But several several task-specific metrics such as QBLU or QRouge also do not capture these changes. Yeah, and the overall takeaway from our paper is that we notice a pattern where different metrics have different skills. And if we just take, for example, the case of image captioning, we have some of the state-of-the-art metrics like SPICE and Wilbert score, which show a complementary behavior on the set of perturbations that we have here. So this opens up interesting avenues for future research where different automatic metrics could be combined to take advantage of their relative strengths. So some, for example, if we want to use, if we want to learn some weightage over all of these metrics so that some combination of them might be able to capture certain criteria in a better way. Yeah, I think with that I'll stop my talk and I can take any questions.
Thanks, Ananya, for the great talk. So if there are any questions, please raise your hand and I'll allow you to talk. Yeah, please go ahead, Sanya.
Yes, so I have a question that whenever you have used human judgments, so how have you ensured consistency between the human annotators? Because people can have very different judgments of what kind of text is more correct or more fluent, etc.
Yeah, thanks for the question. Yeah, actually, that's a important point. I mean, we have used certain data sets or certain pre-existing human evaluations, but we have done that only after checking the correlation values that they report or the inter-annotator agreement values that they report. What they do is they compute this kappa score, which is something like 0.7 in the data sets that we use. There are a couple of data sets that don't report this agreement score, but they report the technique that they use to mine, that they use to ensure that the data that they collect, the human data that they collect, is of high quality. So, for example, they do multiple rounds of collection, and if two humans disagree on something, they encourage them to discuss and arrive at a score. And then in the second round, they again verify if they're if the scores they provide are the same or not. And yeah, there are more techniques of that. I'll also post link to one survey paper which talks about these various techniques used to ensure human annotations are correct.
Okay, thank you.
Thanks, Ananya, once again. So if there are more questions, please post them in the Q&A box and I request Ananya to answer them. Thank you. Okay, so we'll go to the next talk now. Yeah, so all of us know the pigeonhole principle, right? So if you have 7 pigeons but only 6 holes, then one hole should have at least 2 pigeons. So you must have seen in the flyers that there are 7 talks but only 6 speakers. So now there should be 1 speaker with 2 talks, and that is going to be Dev, who will we'll invite Dev again for the second talk in the evening. And this is going to be on winner determination from active pairwise comparisons. So this is a paper that will be presented at the International Conference on Data Mining shortly. Dev, over to you.
Yeah, thanks, sir. Yeah, so as sir mentioned, right, I'll present our work on PARWIS, which is an algorithm for winner determination from active pairwise comparisons under a shoestring budget. Yeah, this project was primarily done by me and Professor Arun, and yeah, let's see how it goes. So what's the problem, right? Again, so it's pairwise comparisons, and there's going to be a lot of common things that we are going to discuss, which is already discussed by Vishnu, but I'll have like a different way of looking at things. He had a more theoretical view, I have a more empirical view of things. Yeah, so we have given a bunch of items, let's say n, and our goal is to determine who is the topper among the set of items, right? And all you are allowed to do is query pairwise comparisons to a bunch of, let's say, crowd annotators, and they'll return some item, let's say among I and j, they'll return some item, and then based on that you can again decide what you want to query, and they'll return some item, and so on. And based on these observations, you're going to find what is the best ranked item, or who is the topper among these set of items, right? So a lot of questions come to mind. The first one of them is that why pairwise comparisons, right? So as Vishnu also pointed out, they are much more simpler than giving a complete ranking, right? So let's say you are asked to give preferences for movies, then it's much more simpler for you to decide between 2 movies rather than give a ranking over, say, a set of 20 movies, right? And the other reason is that it's also more natural than individual scores, right? Because individual scores tend to have diverse scales. So let's just consider our favorite restaurant rating apps like Zomato or Swiggy, and then some place which you are frequently visiting or that you like, you will rate it 4, but then somebody else will rate it 3.5 and someone else will rate it 4.5, and maybe it so turns out that all 3 of you rate it unequally, but you're friends and you like the same place. So pairwise comparisons in this sense are more natural than individual scores. So given all of this setup, the first question that comes to mind is that isn't this problem already solved before, right? So the simplest algorithm that is out there for this particular problem is the select algorithm, and it also gives a state-of-the-art results, right? So what you do for the select algorithm is this: you have a bunch of items, you'll pair them up randomly. Once you have paired them up randomly, you'll compare each pair m number of times, and now based on these m votes, whoever wins the majority of times, you'll promote them to the next level. Again, you'll compare pairs of items randomly n number of times. Again, the winners will be promoted to the next level, and so on. So the only constraint over here is m, which is the number of comparisons made between each pair at each level. And you're finally left with one item, which is something that will declare as the winner. If you do this, the sample complexity that you get, which is how many votes will you require to arrive upon the winner, can be bounded as follows, right? So m over here, which is the number of comparisons you make for each pair at each level, can be bounded by the error bound that you desire, log of the number of items that you are considering, and a separation delta 1, s, which just represents the score difference between the top 2 ranked items, right? So we assume that each of these items that we are dealing with has an underlying score based on which they can be sorted and ranked, or the maximum will be the winner, and so on. And the difference between the top ranked item and the second ranked item, the score difference between them is delta, and m is naturally inversely proportional to delta, right? So now just hold on to this equation for a moment. If we only have a shoestring budget, when I say shoestring budget, is that what I mean is that if you have n items, the m value that you have, or the number of votes that you have at each level, is just going to be 2, 3, or some minor value, or some value which is not really a function of n, let's just say. Then your error bound, if you invert it down and if you write it in terms of m, that is going to become vacuous. So over here, what you see is that the error bound versus the budget for your pairwise comparisons for n equals to 100 items that you're dealing with. And as you gradually go on decreasing the m value, the error bound becomes vacuous, and at a point it just becomes, it makes no sense, right? So now this is because of these high delta values which are hiding inside the constant notations, right? So when people write complexity notations, they just write order n log n, but there are these high constants hiding inside the order notation. So then what do we do for shoestring budget, right? The answer is not really simple, but let's start with some basics. So we introduced spectral ranking and the BTL model, both of which have been introduced before, but let's just do it once more. So spectral ranking is this. You have a graph of n items where each item represents a node, and there is an edge between two items if there is a pairwise comparison between both of these items, right? Now you'll take this graph and construct a Markov chain out of this such that the probability that you walk over an edge from I to j is going to be dependent upon your preference of item j over item I. So if you prefer item I, you'll just stay at that particular node in the graph or in the Markov chain. And if you prefer item j, then you'll walk over that edge and go to item j. So if you have such a Markov chain and you take the stationary distribution of this Markov chain, then this is going to capture the underlying scores of each of these items, right? So now if you have the underlying scores of each of these items, you can sort them to get a ranking. You can pick the best item by the maximum score and so on. Now, given that you have this, if you have n log n pairs, which is that if you have collected votes for n log n different pairs, and you have at least log n order log n number of votes per pair, then you can be reasonably confident about your underlying scores for all of these items, which you calculate using spectral ranking algorithm. And to model these pairwise probabilities or pairwise comparison probabilities and the scores for all of these underlying items, we use the BTL model, which is that if you have a W, which is a score vector over all of these set of items, then the probability that an item I beats an item J in any pairwise comparison is simply going to be given by Wi upon Wi plus Wj. So now, given all of this, there's one minute thing that we need, right? So because we are in the active setting, and as I showed you, right, you'll query one pair, you'll get the outcome of that pair, and now that you have that particular outcome, you want to decide what next square you want to query. So you want some form of an iterative updation of your algorithm or some form of iterative updates to your algorithms, right? You don't want to recompute the Markov chain again and again. So for that, we have a simply nice theorem which lets you incrementally update your Markov chain, which you designed for the spectral ranking algorithm, right? So if you have a pair ij over which you observe some vote, say I wins, then you can easily incorporate this particular vote into your Markov chain by making two changes. And then if you apply this equation twice, you can incrementally update your Markov chain as well as your stationary distribution. You don't have to recompute things again and again. So now we have everything in place, right? We have a way to calculate scores for items based on pairwise comparisons. We have a way to iteratively update things. So then our algorithm becomes quite simple, right? So we introduce Parvis, which is broadly divided into two phases. The first phase is the initialization phase. In the initialization phase, because you haven't really seen anything, you want some baseline scores for all of these items, right? Somewhere to start from which you'll start refining things. So the first thing that you'll do is a simple max finding over an array. Pick an item, keep on comparing it until it loses. If it loses, pick the winner. Again, keep on comparing it and so on until your set of items expire. So once you do this, that will take n-1 comparisons. And if you have those n-1 comparisons, run the spectral ranking algorithm and generate the first set of preference scores, stationary distribution scores, and your Markov chain. Now, until your budget expires, which is B, at each step, pick the next pair and incrementally update the Markov chain. So you'll pick the next pair such that it benefits you the highest. You want some way of computing what pair is going to benefit you the highest. Once you have that, pick the next pair and then incrementally update the Markov chain and keep on doing this, keep on refining your estimates. And once you have refined all of your estimates, all you need to do is pick out the item which has the highest score. Right. So now the only question that remains over here is that how do we pick the next pair, right? So how do you decide that what pair is going to benefit you the most? And we decide that based on something we term as the disruption measure. So I'll introduce the disruption measure in this slide. But before that, a motivation to pick the next pair is going to come from two things, right? So first thing is going to be a local effect. Local effect is when if you have, say, a bunch of items and you already have some winner based on whatever estimates you have right now, and you have some other item which is not really compared enough number of times with the current winner, right? So let's say your winner was J, but you compared I and J just once, I being your current winner, and then just for the turn, for the throw of a coin, right? So J lost in that particular pairwise comparison, and now it's being thrown back in the ranking. And because of that, it hasn't really got the chance to rise up in the ranking, and I is your current winner, right? So that is the local effect that we want to capture, in the sense that we want to give each item, which is not the current winner, enough chance so that it can beat the current winner. And there's also the global effect that we want to capture, which is that because we are doing this Markov chain business, or the Markov chain and the stationary distribution computation, it just might be that because two items which are K and L different from Ij have not been compared even of number of times, and because of that, the estimate that we get for the probabilities from our stationary distribution scores and the empirical probability of a particular pair, which is just the number of wins of a particular item over the total number of firm comparisons, both of these will have some difference, right? So I'll repeat this again. The empirical probability for an item Ij is the number of times I wins in a pairwise comparison upon the total number of pairwise comparisons for Ij. That is the empirical estimate, which is what we generally do for, let's say, coin tosses. And there's also the BTL model probability, which we will get after running the spectral ranking procedure based on the scores that we get from there, right? So we have two of these estimates for the same pair, and both of these estimates might differ because some random pair over somewhere is not being compared enough number of times, and that is going to affect everything in the whole chain. So now we want something that is going to capture both of these local effect and the global effect cleverly. But let's just start with a basic objective function, right? So let's try to fit the BTL model with the parameters that we have in hand. So let's say theta are your BTL model scores for each of the items. Over here, let's say theta I, theta j, and so on. And Nij1 over here represents the number of times I beats j in a pairwise comparison. So this is what the data you have based on the pairwise comparisons that you have seen so far. Nij0 is going to be the number of times j beats I, and so on. So your theta I should, in a sense, follow log Nij1, and theta j should, in a sense, follow log Nij0, and we simply follow a least squares objective function to fit both of these. So if you want to fit a least squares objective function for this parameters, we'll take the gradient of that function with respect to theta, equate it to 0, and so on. So the gradient is going to look like this until you have observed some set of pairwise comparisons S. Now let's say you add one more comparison to this set S, right? So you have some set. For that, you fit the least squares objective. You took the gradient, you put it to 0. That is for set S. Now we introduce one more comparison pair to this. And the pair that you introduce to this is Ij1, which is when you compare Ij, I1, and that particular comparison is now being added to the set S. So now if you add that comparison back to this set, the values for Nij1 and Nij1 is going to change. And based on that, your gradient value for that particular point, for that particular theta, is also going to change. So before you added this comparison, your gradient was 0, but now that gradient has a non-zero value, which can be easily computed using the closed form expression. So this value that we compute for the gradient by introducing one more pair is called the disruption measure, or the disruption in the gradient. Now, for a particular pair, there can be two options, right? If you compare Ij, either I will win or j will win. So you can compute the disruptions in both those directions. So you can compute the disruptions when among Ij I wins, and when among Ij j wins. If you compute the disruptions in both of these directions and take a weighted average of both of them, that particular quantity finally is called a disruption measure for one particular objective function, which is the least squares. And if you simplify this particular disruption measure, right, what you will observe is that it captures both of the local effect, which is the number of comparisons for a particular pair Ij, and the global effect, which is alpha Ij plus alpha Ji, alpha being the ratio of the empirical probability that we have over the BTL probability that we calculate using the scores. So what in essence we have done is that we have taken a simple objective function. We have calculated the disruption gradients for that particular objective function by adding one more pair. And once we do that, we find that the disruption that this particular pair creates in this particular objective function is going to capture both of the local effect and the global effect that we want. And the higher the global effect or the higher the local effect that we have for a particular pair, that is going to give us the most information, or that is going to disrupt our scores the most. And that is the pair that we want to pick in our iterative updates, right? So that is exactly what we do. We calculate the disruption measures for a bunch of objective functions. We use log likelihood least squares Markov. You can find more details about all of these objective functions in our paper, but that is essentially what we do. We calculate disruption measures for all of them, and we find that both the log likelihood, both the least squares objective function and the Markov chain objective function capture both of these local effect and the global effects that we are talking about. The log likelihood objective function really doesn't do anything. It just resorts to you picking up the first two items in your current ranking, and after the initialization, it will just end up picking up the first two ranked items after n-1 comparisons up till eternity. So it's not really going to give you any more information beyond that. But both of the least squares objective function and the Markov objective function are going to capture all of the effects that you want, and they're going to provide some insight into how you should proceed. So then to decide what objective function exactly to use, right, we perform experiments. So we take the gesture joke dataset, which is again a preference learning dataset where you have pairwise preferences over a set of 100 jokes. And we run experiments on that, saying that we don't know the underlying preference scores, but all we want to do is that we want to find the joke which has the highest preference score, or which is the funniest for this particular case. And we run our experiments on these algorithms. So what we do is we run the algorithm 100 different times on the gesture joke dataset, and because all of the outcomes that we are going to observe are going to be probabilistic based on the underlying scores, so all of the outcomes are going to be different, right? So in essence, what we observe is that over the 100 different runs, over here we have plotted out the number of times we recovered the top joke. And if you see, the Markov chain objective function gives us the highest values. So the higher the recovery, the better the algorithm. And the Markov chain objective function gives us the highest values, which is closely followed by the least squares objective function. Over here, you have used 100 jokes for the gesture joke dataset, and our budget is also something like a shoestring, right? So you have 200 votes or 300 votes, and the maximum that we went to was 700 votes because we wanted to consider the case of n log n. So 7 was log 100, and then that's where we stopped, right? And we over here, we also model the current state of the art, right, which is the select algorithm, which I showed you before. And our algorithm with the Markov chain objective function, or even with the least squares objective function, beats the state of the art comprehensively over all budgets. To model sanity checks, simple sanity checks for the objective function, right, we also check out random selection policies, which is represented over here in purple, which doesn't really work well, as you can see. Log likelihood, as I mentioned, it only uses the top two items every time. And after a point, it'll just give the same performance, right? Because it's not going to do anything. Any refinement is not going to happen. It'll just stick to the first two items. We also do random versus top in the sense that we take the current winner as one part of the pair that we want to pick, and the other item is going to be randomly picked up from the other n-1 items, which are not really the top at this point. And against all of this, our algorithm, we see that Markov chain objective function and least squares objective function perform the best and give us the highest recovery counts. To model it for the cases where it's not really first, right? So where the winner is not really recovered, we want to also know that what is the reported rank of that particular item, right? Because we are in the spectral ranking domain, and we will be essentially giving out the ranking over the items rather than just giving finding the winner, right? So because we are giving a ranking, we can also find the reported rank of the particular winner that we are looking for. And over there also we observe that the Markov chain objective function gives us the best values. We can also figure out over here what is the true rank of the reported winner, in the sense that whatever winner is reported by the algorithm, how well was it ranked in the original data set. And over there also we observe that Markov chain objective function, over here obviously the value which is closer to 1 is going to be the best value, right? And over here again we observe that the Markov chain objective function is the best performing objective function. So now, given this, Pavis is fixated, right? You'll follow the template that we introduced, and you'll use the Markov chain disruption measure and play along, right? So then we also want to compare it against a bunch of baseline algorithms, right, to show performance of how these baseline algorithms perform in the shoestring domain, and what happens when you do real world experiments in the shoestring domain, right? So we consider the following baseline algorithms. The first one is the select one, which we already discussed before. The other one is multi-sort. So multi-sort essentially runs multiple quick sorts over the set of items that you have, and then Each quicksort will give you a ranking. All of these rankings are then aggregated via Copeland step. The Copeland step was introduced by Vishnu in a talk before. We also consider active ranking, or AR, which is a bandit style successive elimination based algorithm, but it doesn't consider any parameterization for the underlying scores. So it can work for any parameterization. You don't really need it to be BTL. There's also RUCB, which is the relative upper confidence bound algorithm, which is just the basic UCB algorithm extended to the dueling framework, right? So instead of going each bandit separately, you'll dual bandits and then construct your algorithm. And that's the basic idea for the RUCB algorithm. And there's also SECS, which is a slight variant over all of this, which is successive elimination, but the elimination is also based on a carefully designed sparsity condition. You can read more about it in the paper. But essentially what happens is that when you compare all of these algorithms, they all go flat in the shoestring budget. Apart from select, which is still not up to as good as what Pavis is performing, all of the other algorithms go flat. The reason for this is that when you have just a shoestring of votes, all of the bandit-based algorithms are not really giving as refined estimates of the scores as they wanted, right? So in eternity, if you keep on increasing budgets, all of these algorithms will recover the top item with a reasonably high probability. But when you restrict the budget, that's when the reality also shows up for application-based things, right? And that's when we want it really to perform, and all of these don't perform. Obviously, Pavis beats all of the other algorithms comprehensively. The only kink that we observe over here is this one, which is this particular thing where on the budget of 100, we are not the best. And then again, the performance shoots up drastically as you go from budget to 200. The reason for that is that over here, we have just had the phase one of our algorithm, which is completed. We haven't really started the adaptive comparisons from here, right? Only the phase one is completed, and whatever best item that we have, we report it over here. From 100 to 200 is where the first stage of adaptive comparisons kick in, right? So this is where the highest disruption based pairs are selected, and then they are compared. And then we start seeing the performance improvements, and then it just goes on. So you again observe this particular performance for all of the other metrics as well, right? So reported rank of the true winner and true rank of the reported winner. Everywhere, Pavis is the state of the art in the shoestring budget case. So we haven't gone beyond the shoestring budget for all our experiments. And over here, we have presented just the joke data set, but we have 5 real world data sets, which have all different separation values that we tested it out on. And we also have simulated data sets to capture different n values as well. So all the real world data sets have either an n value of 10 or 100, but the simulated data sets have other values of n as well. And based on all of these data sets, we observe a similar trend, seeing that Pavis beats all of the other algorithms in the shoestring case. So moving on, the road ahead is that we want to extend this framework to the top K recovery setting. So over here, we are just recovering the winner, but if you want to, let's say, recover the top K items, can we modify the objective function to select the pairs in some fashion and target the top K recovery? We want theoretical guarantees for recovery. So we know that empirically our algorithm works well, but we want strong theoretical guarantees as well. But it seems to be quite hard at this point of time. And all reviewers also agreed. So we'll see about that. We also want to introduce adversarially corrupted comparisons, in the sense that whenever you query comparisons to crowdsource workers or to, in general, to the open public out there, what happens is that there might be people who might want to game your system, right? So let's say you host your algorithm on something like MDB, and there are people who are Marvel fans and DC fans. So then obviously they will vote for things that they like, or things that they want to win, or things against that they don't want to win, and so on, right? They don't want some things to win, and then they'll adversarially corrupt the comparisons and so on. And then what we want is that we want an algorithm which is robust to all of these adversarially corrupted comparisons. And in a sense, we want to root out all of the malicious people as well. And we also want to consider the dynamic arrival of items, right? So again, going back to the IMDb example, is that if you host your algorithm on something like IMDb, then movies will keep on releasing as your algorithm is working, right? So over here, we are only dealing with a fixed set of items and a fixed set of movies, but you also want to add new movies to your framework as they come along. And to do that, you need some changes, and that's what we want to also explore as a future work. So thank you. And you can also find the GitHub page of our paper, where you can find all the code which was used to simulate all the experiments that you saw over here, and you can replicate all the results over there. And yeah, we have also linked a preprint on Professor Arun's website. Thank you.
Thanks, Dev, for the nice talk. Are there any questions from the audience? Please raise your hand and we'll allow you. Okay, so if there are no questions, or if you have other questions, please type them on the Q&A box later, and I request Dev to answer them. Thanks, Dev, for the talk.
Sure.
Yeah, so maybe I'll please share my screen, and yeah, so so that brings us to the end of the first part of the event today, the workshop. So what we'll do, we'll start the next set of talks at 7:30, but before that, we have something interesting also coming up. We'll right now, after in the next minute or two, we'll start playing a video where if you're a student, or if you're a graduate researcher who's looking to know more about RBCDSAI, so we'll show a video by Professor Ravindran on explaining what is RBCDSAI and what we do here. After that, we have a bunch of spotlight videos, 5-minute each, on some of the interesting papers that have also come out of RBCDSAI this year. So we'll play a recorded video, 5 minutes each, for 4 such videos before we start the next set of talks. So I now request Martina to take over and play the video. Martina, over to you.
Hello everyone, I am Ravindran, a faculty in Computer Science and Engineering at IIT Madras. I also head the Robert Bott Center for Data Science and AI at IITM, one of the largest interdisciplinary AI centers in India. So the center started operations back in 2014 as an interdisciplinary lab for data science, wherein faculty from 6 different departments got together to start this group. And we started off small scale with 3 projects. And today, so we are the Robert Bott Center for Data Science and AI. We started operating in this avatar in 2017. And now we have 28 faculty members, more than double our size, across 10 departments in the institute. And so we have more than 120 plus publications in the past few years, and as well as around 23 different interdisciplinary projects. The various areas that the fundamental research areas that the center looks at, right? So we are having a significant focus on looking at data science and AI applications in various engineering disciplines. And network data is something that arises often both in engineering disciplines and across other areas such as biology, transportation, social media, telecom, and reaction networks. So the idea here is that you're not looking at entities in isolation, but looking at interactions between entities as well. And so our center has one of the largest groups in the country that looks at network data across different disciplines and also take advantage of the synergies that arise. We also have a very large group that looks at deep reinforcement learning. And so we have certainly published extensively in the last few years, and we are the largest group in India. And so we just not do these kind of fundamental research work. At this point, we're starting to make an impact at the global level as well. So some of our recent work, for example, GrabQC, which is query contextualization for automated coding in a medical domain, won the Best Application Paper Award at PAKD 2021 recently. And before that, we had a paper on explaining deep convolutional nets for image classification that won award at WAC-V 2020, one of the top vision conferences, as the best paper award. Apart from these kind of research impact, the work at the center is also have significant societal impact. So we collaborate with multiple governmental bodies as well as NGOs in looking at several socially relevant projects. For example, we helped the Tamil Nadu government set up the CM helpline, and also we work with closely on the COVID war room currently. So here are some numbers. So like I mentioned in the beginning, so we have about 28 faculty spread across 10 departments who are part of the center. And we have about 80 plus researchers, 6 of them who are postdocs, and about 10 postbaccalaureate fellows are there currently, and about 50 plus research scholars both at PhD and master's level. And as I mentioned earlier, we have 120 plus papers that have come out, of which more than 50 have high impact conferences like A-star rank conferences and very high impact factor journals. And we have collaborations across the board. This is like just the mind-boggling number of collaborations that we have both in the industry and NGOs. And we can also see our international collaboration footprint is fairly large going now. And hopefully we are looking to expand this much further as we go down the years, right? So one of the new research initiatives that we have launched this year is looking at what we call as deployable AI. So doing AI research in the laboratory is fine, but when you actually try to deploy it in the field, a lot of things that could go wrong. So we're looking at it, multiple facets of this, looking at fairness and social relevance of AI, explainability, transfer learning, right, and also privacy and safety in AI, and also AI on the edge. And RBCDSAI is on social media and it's on the web. And please look up our YouTube channel, our Twitter channel, and everything for more information about us. So do write to us if you're interested in joining us or interested in knowing more about the center. We always welcome them. Thank you.
Okay, so that was the introductory video about RBCDSAI. So before we move on to the spotlight videos, if any of you in the audience have any questions about RBCDSAI or how you can collaborate with us and things like that, please let us know, and we'll be happy to answer. Are there any specific questions at this point? Yeah. Go ahead, Abhishek.
Good evening, sir.
Good evening.
So I have a question. Can BTech student get a research, or can BTech student work in RBCDSAI just for having a research?
Sure. So so we have the post-bac fellowship, which is like just after you complete your BTech. So you can actually formally apply to RBCDSAI, and where you'll be able to work with some professors here on some projects of interest. So that is one definite opportunity. Are you asking for BTech students who have not yet graduated?
Yes, sir. I am asking for just people who are doing just the BTech. So can this, suppose for the second year or third year students, can they participate in RBCDSAI? Just asking for that, sir.
Sure. So there is we don't have like a formal program per se, but I think feel free to look at the projects that are happening at the center, and if you find something interesting, you can perhaps write to the faculty involved, and if they have a position where they can accommodate a BTech student, sure, why not? Yeah, you can do that.
Actually, sir, I'm interested in the machine learning part, so I was thinking of that. Just
sure, yeah, definitely. So I suggest you look at the RBCDSAI webpage to see the current projects, some of the current projects at the center, and see if something interests you there.
okay. Thank you, sir.
Sure, thanks. Any other questions? Okay. Okay, so what we can do is, what we'll do is we'll go to the next part of the program. So which is the spotlight videos, and we have spotlight videos by of 4 different papers authored by Bharat Manvi, Karthik V, Rajan Kumar Soni, and Pawan Ravishankar. So I think some of the speakers are also here. So in case you have any questions about these talks, you can either type them in the question and answers box, or you can also reach out to these speakers. So maybe we can start. It's just 7-8, but I think we can get started. Martina, if you want to play these videos.
Hi, I am Bharat Manvi. Today I am going to present on simultaneous beamforming and trajectory tracking in a multi-agent formation. So let's get started. So let me start with the motivation for the problem. Say there are a bunch of agents which are collecting some information, which have a isotropic antennas on them, and there is a direction in which the receiver is present, and the information which they are collecting on ground, they want to send that information towards a receiver which is very far away, and also these agents take the commands from the faraway receiver to operate. So now the goal is to make sure that the energy of the information which reaches the receiver is high enough to reconstruct the signal. Similarly, the case with the commands, so that the commands can be reconstructed. So next we have a signal transmission part, where we assume that each of the signal is sinusoidal signal, and also the command signal is a sinusoidal signal. So, and when this signal is transmitted through the channel, it is attenuated and time delayed, and there will be some noise added. So instead of taking a random arrangement, when we take the arrangement of the antennas or the agents as a regular polygon, say hexagon in this case, then we'll have a beam pattern as shown here, and there will be a maximum transmission axis which is as shown here. So, and one of the control goal is to align this maximum transmission towards the receiver. Okay. So now suppose when this maximum transmission axis is aligned, then the maximum power is reached at the receiver. So similarly, which increases the signal to noise ratio of that signal. So now we come to the problem setup, where suppose say that the formation, the polygonal formation which we call it, is aligned, that the maximum transmission axis is aligned towards the receiver initially, and the centroid of this regular polygonal formation is tracking a trajectory RD. So when the formation, when the agent, the centroid tracks the trajectory, we need to make sure that the maximum transmission axis is always aligned towards the receiver for the maximum signal to noise ratio. So now this part, the problem has two parts. One is the formation control, where the agents come to that polygonal formation, and other is to align this maximum transmission axis towards the receiver. So now when this agents come to the formation, we can treat it as a planar rigid body, a virtual planar rigid body, and the center of gravity of this rigid body is coincides with the centroid of this regular polygon. So here we have a rotational matrix representing the rotation of this rigid body in the inertial frame I, and we will use the control omega f to align the maximum transmission axis towards the receiver using the rotational kinematics of the planar rigid body. So now we proposed cascaded control law, which comprises of the formation control law and the geometric control law, which I explained earlier. So now we extend this control to the quadrotor model, where we in the lab we took the quadrotor as the crazy fly as shown here, and we proposed a cascaded control law using the Ross for the crazy fly. So our cascaded control law will generate the trajectories for each of the quadrotors in the arena. So and the previous present positions of the quadrotors are fed into the cascaded control. This is how the cascaded control law is useful in the formation control and the alignment of the maximum transmission axis as shown here. So now here the control law which we have proposed is being implemented on the quadrotors as shown here. As explained earlier, we can see that the formation here we consider is a square formation, and from the side view we can see that there is a tilt which explains that the maximum transmission axis is aligned. So yeah, thank you.
Hello everyone, welcome to the 11th workshop on recent progress in data science and AI. Today I'm happy to be presenting our work, a joint training framework for open world knowledge graph embeddings. In the last few years, knowledge graph embeddings have taken off as a popular approach to encode information for a variety of downstream tasks like natural language inference, question answering, and dialogue generation. As knowledge bases expand, we are presented with newer open world entities, often with textual descriptions. As a result, applications or tasks that rely on knowledge graph embeddings require approaches to embed these new entities. We want such a model to train embeddings for open world KG entities, and we want certain essential properties to be satisfied. We want our triple scoring function and hence our ranking function to be efficient. Since recent studies have observed that different KG embedding approaches like transient and complex are suitable for different applications, we want our technique to be modular. We want our model to work on a variety of KG datasets, regardless of their description length. And most importantly, we want the modules of our approach to be trained jointly, as recent studies have shown that joint techniques are significantly improved geometric properties. This diagram shows the overall framework of our model. We have three modules, chiefly the description embedding module, the knowledge graph embedding module, and the projection module. Our framework uses knowledge graph embedding laws, projection laws, cross KG completion laws, and regularization laws. When our descriptions are short, we just average their word embeddings to encode them and minimize this loss to train folk. On the other hand, when our descriptions are long, we use Roberta, a large transformer model, to encode our descriptions. As it takes a while to train, we split the training out into two phases, where we train the KG embedding module followed by our description and projection modules. So these are some of our results. So we observe here that folk significantly outperforms baselines on open world knowledge graph completion with an average mean reciprocal rank improvement of 35%. On short descriptions as well, we outperform our baselines, and we note here that both ways of encoding descriptions here perform similarly. On the topic of geometric properties as well, we notice that embeddings induced using folk, which are the embeddings in red in these diagrams, are more homogeneous with the pre-existing KG embeddings, the embeddings in blue, whereas the embeddings trained using OWE, which is one of our baselines, cluster separately. We also report two metrics, eigenvalue similarity and hubness, to check if the two spaces are aligned. And here as well, we can see that folk performs much better. Thank you. Please do reach out to me for more details, and Hope you have a great time at the Robert Bosch Center's workshop.
Hi all, I am Rajan Kumar Soni. I will be presenting the paper entitled Metric Learning for Comparison of HMMs using Graph Neural Networks. HMMs are typically used to characterize sequence data in application domains like posture recognition, assessing fine motor skills, and genomics. This implies that an ability to compare HMMs can help us in answering questions such as these. There exist some metrics in the literature to compare HMMs. Some of them are graph matching based metric computes the similarity between two HMMs as the similarity between their adjacency structures. Cross likelihood based metrics approximates the distance between two HMMs based on the likelihoods of the HMMs to generate both the reference sequences. In matrix factorization based metric, the feature matrices of the HMMs are factorized to obtain latent embeddings. The distance between the two HMMs is then computed as the distance between their embeddings. Out of these metrics, the first and the second metrics are structure-based and behavior-based metrics respectively, whereas the third metric considers both structure and behavior. However, there are several demerits with these metrics, such as these metrics fail in case two HMMs have similar structure yet different behavior. Further, the graph matching based metrics demands an intractable computational footprint for large HMMs. Also, the accuracy of behavior based metrics depends on the quality and noise-free nature of the reference sequence used. Further, no existing research is available for leveraging GNNs for learning embeddings of HMMs. In a nutshell, we propose graph variational autoencoder based and deep pooling GNN based architectures respectively for the task agnostic and task aware settings. Finally, we also evaluate the sanity of these embeddings through extrinsic tasks. This is the architecture of graph variational autoencoder that you abbreviated as GVAE, which encodes the structure and the emission features of a HMM into a generative, regularized, and behavior preserving latent space, which is characterized by the parameters mu cap and sigma cap square. The decoder reconstructs the adjacency structure of the HMMs as the self product of the embedding sampled from the latent space. However, the embeddings learned by GVAE are flat, as at one stroke, we aggregate the individual node embeddings to obtain the HMM embedding. This leads to losing important localized behavioral patterns. To address this demerit, we propose using a deep pooling based GNN which learns the HMM embedding by hierarchically aggregating the embeddings of localized spectral clusters. The deep pooling network comprises a stack of layers with each layer having two GNNs, one for learning the embedding and other for learning the spectral subclusters. Between the layers, we have a deep pooling layer which infers the embedding of each node in the quotient graph. We evaluated the embeddings with respect to clustering and classification tasks. We picked the embeddings against 6 baseline metrics, with FSDD as the reference data sets. As could be observed from the graphs, the proposed metrics perform better than the baselines at both the single linkage and complete linkage clustering tasks, even when the size of the training set is less. The performance metrics used are purity, trend index, and NMI. We designed the second set of experiments to assess the ability of the proposed metrics to recognize the similarity between two HMMs, having different number of states yet similar behavior. As depicted in these plots, the proposed metrics are quite successful related to the baselines. This slide shows a visualization of the embeddings learned by the proposed GNN architectures. Deep pooling based embeddings are more discriminative than the GVAE based embeddings, which is not surprising as the representations are class aware. Both the learned embeddings perform very well with respect to the classification task, as can be seen in the figure. To sum up, deep pooling outperforms other metrics categorically. Other significant observations are distance metrics based on learned embeddings typically yield better accuracy than those generated by structural baselines. GVAE-based embeddings are effective even in tasks where the datasets contains structurally dissimilar yet behaviorally similar HMMs. Distance metrics learned through deep pooling perform better than the structure-agnostic flat embeddings, while other metrics falter when used with single linkage MST clustering algorithm. Deep pooling exhibits a robust performance. Future work will include extending the proposed techniques for other temporal behavioral models. Thank you.
Approach for unfair edge prioritization and discrimination removal. This was a joint work with Pranshu Malviya, and both of us were guided by Professor Balaram and Ravindra while we were at IIT Madras. Objective of our work is twofold. Firstly, we attempt to mitigate the unfairness in the data generation procedure towards a subset of sensitive attributes. Secondly, the objective is to debias the data distribution post the data generation procedure. So we use the notion of a causal Bayesian network to qualitatively model the dataset generation procedure, wherein each particular node is generated by its parents. For instance, the judicial bail attribute is generated by the racial attribute, the education attribute, the criminal history attribute, the employment attribute, and the gender attribute. The challenge comes in mitigating the unfairness with limited resources. So that's the key point here. We have limited resources to mitigate the unfairness in the decision-making system. So for instance, if the decision is to grant a bail, and we are interested in identifying how much of unfairness is present in this particular decision towards the African American community, qualitatively we know for a fact that the unfairness propagates along the direct edges and the indirect paths from the race to the judicial decision attribute, that is the R to J, R to E to J, and R to T to J. But how much of unfairness actually underlies these unfair edges so that we can take tangible steps to mitigate the unfairness? We quantify what is known as edge unfairness. We do that by first quantifying the edge flow and then decomposing the conditional probability of any given node, its parents, into these edge flows, and then quantifying the edge unfairness. In simple terms, what edge flow is, what is the belief of a particular node, say the judicial decision, due to its parental node, say its racial node, along a particular edge. So the racial attribute influences the judicial attribute along the direct edges and along the indirect edges. So what the edge flow does is it quantifies just the influence along the direct edge. And using the edge flow, we then decompose the conditional probability distribution of the judicial bail condition on all its nodes into the edge flow quantities. And then we quantify the edge unfairness. So once we quantify the edge unfairness of, say, like there is 0.8 edge unfairness in race to judicial bail, and there is like 0.2 amount of edge unfairness in race to education, then naturally one can direct policy initiatives towards mitigating unfairness underlying the race to judicial bail decision, which could be increasing the representation of the judges belonging to a particular racial group. So this is how we decompose the conditional probability distribution into the influences along the fair edges and the unfair edges subjected to the probability constraints. And once the decomposition is done, we calculate the edge unfairness as the conditional probability values with the edge flow flowing along that particular edge E, and without that the edge flow flowing along the particular edge E. Now, once we formulate what is known as edge unfairness, we then derive the result that the cumulative unfairness in any particular decision, say the judicial bail decision, towards the African American community, which is formalized by the node S here, is non-existent when the edge unfairness is eliminated in all the unfair edges. So this result seems to be trivial in the linear case because it's equivalent to just removing all the unfair edges, but it is not so in the non-linear case, wherein the cumulative unfairness cannot be expressed in terms of edge unfairness in the closed form. So we upper bound the cumulative unfairness by another quantity that depends on the edge unfairness and show that the upper bound goes to 0 as you eliminate the edge unfairness. So then we quantify the potential to mitigate cumulative unfairness when edge unfairness is mitigated. We then prioritize the unfair edges based on its edge unfairness and its potential to mitigate the cumulative unfairness. Then we debias the data distribution once the data is generated with the data utility term and the sum of the edge unfairness as the objective function. This eliminates the exponentially growing constraints as the number of sensitive attributes increases. The key experiment we perform in this paper is to show that decreasing the cumulative upper bound indeed decreases the mod of the cumulative unfairness. The theorem that we proved theoretically shows that setting the upper bound to 0 indeed makes the mod of the cumulative unfairness to 0, but does not discuss the relationships. So in conclusion, We have quantified edge unfairness, we have quantified the potential to mitigate the cumulative unfairness, and using these two quantities, we have prioritized the unfair edges for mitigation process, and then finally remove discriminations once the data has been generated.
Okay, great. Thanks, Martina. So those were the spotlight talks. Let me share my screen. So we now come to the second part of the workshop. So we have three more exciting talks up. So the next talk would be on semi-supervised deep learning for multiplex networks. This would be by Anushya Mitra. And this was a paper in KDD 2021. I guess we can wait for a minute before we get started. Anushya, maybe you can set up your presentation if you are around.
Is my screen visible?
Not yet.
Now?
Yes, I can see your screen now.
Okay. Should I start?
Yes, Anushya, maybe you can get started.
Yeah. Hello everyone, I am Anusha Mitra, a senior PhD scholar from Indian Institute of Technology, Guwahati, and I welcome you all to the presentation of my paper titled Semi-Supervised Deep Learning for Multiplex Networks. This is a collaboration work among Indian Institute of Technology, Guwahati, McGill University, Mila, Ohio State University, Indian Institute of Technology, Madras, and Robert Bosch Center for Data Science and Artificial Intelligence. So to give you a background on multiplex networks, let us first understand the structure of multiplex networks by a few real world examples. So multiplex networks are complex graph structures in which a set of entities are connected to each other via multiple types of relation. And given few examples of multiplex networks, in the first figure we see a snapshot of the London public transportation system. So a set of regions in the city are connected to each other via various means of transportations, say tube, DLR, overground, etc. And the connection weights within a layer indicate the transportation cost. Whether and the same nodes across the layer represent identical parts of the city, the cross edges represent like change of mode of transportation, and the weight associated with the cross edges represent the switching cost of transportation from one mean of transportation to another. So studying such networks helps us designing traffic management strategies for smart cities. Here in the second example, we see neuronal interaction inside an insect brain. Neurons interact with each other via chemical connections or synaptic connection, and chemical connections are known as synaptic connection. Research suggests that neurons communicate through extrasynaptic layers through a range of analysis of how one region of brain activates another region or functionally dependent on another region. This layer-wise analysis of neuronal connections and cross-layer association shed more light on complex brain structures and their functions. We also see multiplexes of genes where genes are interacting among them via co-expression protein interaction pathway. So we see intertwined two multiplexes, and they are related to each other by cross.
Anusha, your voice is breaking. Is there a...
We can even model social interactions like we see Twitter in multiplex way.
Anusha,
One
can you hear us?
typical way to model the
Anusha,
among the
Anusha,
users via in terms of tweets, retweets, replies, mentions, but also see based on their interest in certain social issues like refugees, education, economy, women's rights. We can model the user interaction in layer-wise manner, where user interaction within a layer would that users are interested in a particular societal topic and how they are important to other. Yes.
Anusha, your voice is breaking. Is there an issue with your network? Hello, can you hear us? Anusha, are you still on the call? Okay. Anusha? Okay, so let me quickly check if we can talk with her. By the way, is Rohan Safal around? Okay, so I think he has not joined yet. So let's wait for a minute to see if Anushya can.
Hello.
Yeah, Anushya, can you hear us?
Yes, sir.
Okay.
Are you able to see my screen?
We were able to see your screen, but your voice was breaking. But now it seems okay. Is there a network issue, or is that fine?
I guess so. Sorry, sir.
Yeah, so you can continue now. It seems fine.
Okay. So like this, we can also model the social interactions in multiplex way. So these are few real world examples of multiplex modeling. Even we see a few other real life examples like collaboration citation networks, trade networks, financial system, molecular interaction, recommender system. This kind of systems can be naturally modeled in multiplex way. So this is a detailed example of how we formulate the layer-wise modeling task of multiplex networks. We see one example multiplex network of paper-to-paper association, where the blue layer indicates the co-authorship information, like two papers will be associated if they have common author. And the green one is based on the citation relationship. If one paper cites another paper, then there will be age between them. And if two papers are related to same field of study, then we can associate them by cross-layer edges based on common subjects. So this is one example, two-layer multiplex network. And the within their interactions are called as intra-layer adjacencies. And this kind of multi-layer architecture we often model in form of supra-adjacency matrix like this, where it comprises of component adjacencies based on the main diagonal. We have the within layer adjacencies like intra-layer adjacencies of common co-authorship or citation relation, and along the off-diagonal elements we have cross-layer association or inter-layer adjacency. So we have a multiplex graph G of R layers, G1 to GR, assuming we have a set of R number of relations in the underlying graph, and each relational graph can be described via this triplet, where V is set of nodes which is common among all the relational layers, and AR is adjacency matrix pertaining to the relation R, and it is a set of intra-layer and inter-layer adjacencies which is related to the relation R. And X is node feature matrix or node attribute matrix, assuming each node can be associated with a set of F number of features. So this is how the notations look like for multiplex networks. And we are interested in a transactive setup for semi-supervised learning. That is, we have partially labeled graph and we want to predict labels for all the unlabeled nodes. Given a multiplex graph G, a label set Q and set of labeled nodes L. We also have supervision knowledge or ground truth label assignment matrix Y. The task is to predict labels for all the unlabeled nodes U. For efficient semi-supervised learning on multiplex graphs, it is essential that we learn a low d-dimensional node embedding. Now, also, we wish to encode in this paper, in this work, the higher order non-trivial global graph structures, say walks or relational paths or motifs, any kind of subgraph, any kind of non-trivial global graph structure into the learned node representation. In general, the network representation learning methods encode only the local contextual information surrounding a node of interest to learn node representation. But of late, significant number of recent studies advocate for learning global graph representation beside encoding the local neighborhood context, since it facilitates learning of more discriminating and enriching node representations. So this is our goal. We also want to encode relevant local global structural characteristics of the underlying graph along with supervision information available. Now, what are the challenges and research gaps in this setting? We have different learning paradigms, random walk-based methods, metric factorization-based methods, graph neural networks to learn network representations. Studies have also tried to capture various aspects of a multiplex network, say local global network structures, cross-layer associations, node features, label information, or coming up with any effective embedding aggregation strategy across the layers. But limited number of attempts have been made so far to effectively capture global structures in a multiplex network. So random walks and GNNs claim to capture the global information by capturing the k-hop local context for node. But this is a trivial way to like incorporate the global graph structure. In real world, the graph structures that we want to capture can be very different, ranging from paths to walks to motifs, etc. So merely capturing k-hop local context cannot give us the encoded into the local network node representations. And then matrix factorization methods are not scalable. We also have in multi-graph learning setting, structural pooling, unpooling methods, but when it comes to multiplex networks, they do not capture cross-network association, or they lack in effective aggregation strategies. So this is the main drawback or the research gap in learning structure-aware network representation in multiplex networks. That is, GNN and Infomax-based methods capture global structure in unsupervised trivial ways, respectively. So we especially mention about Infomax-based learning strategy that provides a way to incorporate global graph information into the learned node embeddings by maximizing the average mutual information between a node's local context and a shared global context, global graph context. So let us see how in typical setup, Infomax principle is applied to graph. So in a typical Infomax-based learning setup, the methods naively maximize the mutual information of a node's local representation with a shared common global graph context. So this common, in this paper, Deep Graph Infomax, the authors learn node representation, which is local surrounding the node of interest, and then aggregate all the local node context to form a single global graph summary S, which is common to all. And then using a discriminator D, they try to maximize the mutual information between the local node representation HI and this common global graph summary S. Minimizing this kind of noise contrastive estimation loss is basically maximizing the mutual information between this local and global graph context. But it trivially encodes lots of noisy information found across all the nodes neighborhood, because the global graph summary is only one, which is shared. So let us see how Infomax principle is applied to multigraph setting. We have state-of-the-art paper, Deep Multigraph Infomax, this paper. So here we have a multiplex graph, and relation-specific node embeddings are learned in a layer-wise manner, which are like HIs, and then upon naively aggregating all the local node information, we get one graph summary. And a discriminator tries to discriminate between the local and global node representation. This is one universal discriminator which is common to all, so that it can discriminate across the R layers what are the true local global graph context as opposed to the false or corrupted local global graph context. But the drawback of this work is it naively aggregates the node representation via one, say, mean pooling based readout function. And in this way, lots of noisy information are encoded. Here we argue that a contextualized representation of the global graph information facilitates encoding relevant non-trivial shared information. That is, we personalize the global graph summary for a node. To give you an example, here we can see a graph structure, and our subject of interest are this red node and blue node. Red node belongs to this C2 graph cluster, and this blue node belongs to C2, C3, and C1 cluster. Now, based on this structure, like the structure of subgraphs centered around these nodes are differently connected to the rest of the graph. So we'll have different non-local network measures such as betweenness centrality, or average shortest path length from the central node, or participation coefficient. Such non-local network measures will be different for this red node and blue node, because the blue node is more centered and the red node is at the end of this network whisker. So it is very naive way to actually assume a shared global graph summary for these two nodes, whether a global graph summary for red node should be more inclined to the cluster C2 representation, and the global graph context for this blue node should be more inclined towards this C2, C1, C2, and C3 cluster rather than incorporating C4. So here we propose structure-aware Infomax principle. We personalize the global graph context for all the nodes in the network. And as a mean to do that, we learn clusters, logical grouping of nodes in a way to generate contextualized global graph summary for each node. How that we'll see in the following slides. So these are our contributions. We propose a novel joint node cluster representation learning framework that uses a structure-aware Infomax principle. And this structure-aware Infomax principle considers node contextualized global graph representation as opposed to a single shared global graph summary. To generate this node contextualized global graph representation, we learn label-informed clusters. So this is the end-to-end architecture of our proposed method, semi-supervised deep cluster multiplex. And roughly the learning happens in these 5 stages. Like first, we learn relation-specific node representation via GCN in each layer. We generate the node embeddings and then encode the label-informed clusters via learning a cluster set of cluster embeddings and this node to cluster association matrix simultaneously. Then we generate cluster-aware graph summaries for each node and use a discriminator to discriminate between pair of local global graph contexts from corrupted ones. And since we also wish to capture the diverse structural aspects of a multiplex graph, we also incorporate the cross HSY cross graph regularization. Also, we have attentive aggregation strategy to combine the nodes, relation-specific node embeddings to a single node representation. And at the end, we have a semi-supervision loss. So these are few of the building blocks of this architecture. So we have relational GCN that captures M local neighborhood context. So here is M hop, M layer, hidden layers, followed by dropout layer to prevent from overfitting, and followed by one nonlinear activation function, which generates the node embeddings. And then with the generated node embeddings, we randomly initialize the cluster embeddings, and via a projection layer followed by softmax activation function, we learn node to cluster association matrix that gives us a probability of the propensity with which a node belongs to a set of clusters. And to learn this cluster, we use label correlation similarity kernel defined between the label node. We argue that this is a powerful way to capture powerful kind of node proximity, because we can associate to nodes who are at like longer hop distance than M hop that we are considering in our GCN learning phase. Also, even if two nodes are not connected in the underlying graph, but they do have label similarity, we can still make a connection and form logical groupings of nodes. So via this unnormalized graph Laplacian regularization, we learn the node cluster membership from the label correlation similarity matrix. And then to ensure that we have less noisy clusters or less overlapping clusters, we have this orthogonality constraint. Now, given we have learned the cluster membership matrix, we can generate a contextualized global graph summary for each node by a weighted linear combination of a node's propensity of belonging to a set of cluster multiplied by the respective cluster embedding. So this gives us a personalized global graph summary for a node, and then this global context and local context are sent to a discriminator that scores a positive local global context higher than n number of corrupted local global context based on such bilinear scoring. And to capture other diverse aspects, we have incorporated cross edges via cross relation regularization. Then we attentively aggregate the node embeddings, and at the end we have semi-supervision loss, resulting in a final architecture like this. So these are the research questions. We want to understand how well this SSTCM perform on a variety of downstream tasks, say node classification, clustering, or similarity search, or how it can perform as compared to a diverse range of multi-graph network representation like baselines. And as we are learning the level-informed clusters, how good they are in improving the in-task performance, and at all if the personalized global graph summaries are useful as compared to a common shared graph summary. So this is our experiment setup. We have like from diverse domains, we have data sets that have features or no features. They can be multi-class or multi-label. From the various domain like bioinformatics, bibliography, movie networks, social networks, or recommender systems. And then we have these diverge state-of-the-art baselines from various multi-graph settings, and we compare them based on what aspects of multiplex network they are capable of capturing. Whether the node attributes within network, cross-network structure, the global structures, the supervision knowledge, and whether they have any effective aggregation strategies. So we see that SSTCM incorporates all the diverse aspects of a multiplex network as compared to the other competing method. So SSTCM gives state-of-the-art performance on node classification clustering task. We see that, so this is our first research question that we aim to address. We interpret the node classification result in terms of micro-F1 score, and we calculate an NMI normalized mutual information score for the clustering task. We see SSTCM for the node classification task beats all the methods, DMGI, deep multiplex graph Infomax being the second, but not on Flickr and SLAP. And even for the clustering task, SSTCM outperforms all the competing methods by a large margin, except this IMDb multi-label dataset. Even we observe that SSTCM's label-informed node clustering strategy improves similarity search result. In a similarity search setup, we basically compute the cosine similarity among all pairs of nodes, and then for each node as a query, we retrieve top k relevant nodes based on the cosine similarity, and see what fraction of the retrieved nodes actually have the same set of labels as the query node. So since SSTCM is like grouping the nodes based on label correlation, so we see that SSTCM outperforms all the methods in this similarity search setup. And we also see that all the semi-supervised learning methods like MGCN, RGCN, heterogeneous attentive network, HAN, even DMGI are doing good in comparison to merely unsupervised method like deep multiplex graph clustering, DMGC. And also we see that so in this ablation study, we want to find out the contribution of the label-informed clusters. So we vary the number of clusters K in some ranges and find out like how it is affecting the clustering results and even node classification result. So here I want to distinguish between two kind of NMI score. We have normal NMI score that we generate node embeddings and give it to clustering algorithms like K-means and C-means to compute the normalized mutual information score. And then since we are learning the clusters, cluster matrix, node cluster association, we get the cluster prediction from the learned matrix as well. And we call this, and comparing it to the ground truth labels, we call this NMI-C. So we see as we are as the number of clusters are increasing, we also see in relation-wise manner the NMI scores are improving. NMIC scores are improving. Even we see in other data set also. So this gives us proof that, okay, level-informed clusters are actually improving the in-task performance. We also plot the node embeddings of semi-supervised computing methods via TSNE visualization, and we see the SSDCM gives us well-separated homophilous clusters of nodes. Here, the color code indicates the functional classes, and this we have plotted for Flickr dataset, which has 7 functional classes, and we see well-separated homophilous clusters for SSDCM as compared to the other methods. And this is the most important ablation study in our work, because we wanted to find out how good is the node contextualized global graph summary as compared to the common shared global graph summary. So we introduced a number of variants of SSDCM where we kept the cluster learning part intact and used various structure-aware pooling strategies like top-cave pool, structure-aware attentive graph pool, adaptive structure-aware pooling, ASAP pool, and we compare these variants with our cluster-aware graph summary generation. So this discriminator uses a single structure-aware global graph summary, and these are the results which are better than DMGI, but not as good as SSDCM. And we see personalization or contextualization of the global graph summary for the nodes actually improves the in-task performance. So this gives us proof that this node contextualized global graph summary is beneficial. And to conclude, SSDCM incorporates a unique structure-aware Infomax-based learning strategy and learns contextualized global graph summaries to jointly model nodes and clusters. And in future, we'll be interested to see, like, if we could, we can generalize the SSDCM framework for other multi-layer graphs where we may have various types of node in each layer as like compared to multiplex setting. And even if we could generalize SSDCM for simple homogeneous graphs. And what if we, instead of label our structural Infomax, we have unsupervised clustering criteria for our structure-aware Infomax? Will they have similar benefits? Or if we could compare the performances of semi-supervised and unsupervised structure-aware Infomax? So this concludes my presentation. Any questions are welcome.
Thanks, Anuswa, for the talk. So in the interest of time, if there are questions, I would like the attendees to paste them in the Q&A box, and Anuswa, you can respond to them there. Thank you again for the talk.
Yes, sir.
So we'll go to the next presentation now. So this would be on sample efficient ensemble reinforcement learning, and will be presented by Rohan Zafal. So this is a paper that was presented at AMAS 2021 earlier this year. Yeah, over to you, Rohan.
Thank you.
Rohan, somebody is celebrating a belated Diwali behind you.
No, sir. So actually, it's raining heavily here, so I've tried to be in the quietest place. But yeah, this is the best I can do at this point. It's kind of raining cats and dogs here. So I'll try to be as loud as possible, and in case there's if something's inaudible, I'll be happy to come back and sort of reiterate the same questions again. So
are you using a headphone mic with the?
Yeah, I'm using that, but it's still pretty loud here.
Okay.
Yeah, so apologies in advance for the background noise. So yeah, I'll just get started. So I'll be presenting sample efficient ensemble reinforcement learning, also known as SERL. This is a joint work with Dr. Ravindran, Deepak Samudigire, who is currently at Facebook, Sasikant Avancha, who is at Parallel Computing Labs at Intel, and Bharat Kaul, who is also at Parallel Computing Labs at Intel. I'll start with a basic introduction to reinforcement learning, just to sort of give a primer to anyone who's unfamiliar with reinforcement learning. So RL basically deals with the problem of sequential decision making. So it essentially provides a mathematical formalism for an agent to learn from experience. So it basically involves the interaction of an agent with an environment with the main goal of accumulating or maximizing the total reward that it accumulates towards its entire interaction period with the environment. In sort of typically modeling reinforcement learning problems, they're typically formulated as a Markov decision process. And this consists of, a state space S, an action space A, a transition operator, and then R, which is a reward function. So you essentially would have a state, an agent that basically starts at some state ST. The agent basically takes an action AT at the state, using a policy pi, and then essentially receives the reward R, and then transitions to the next state ST plus 1 based on some transition probability P. So this is typically the kind of a framework for solving RL problems. And although this is not essentially the only way to sort of formulate an RL problem, there are other things like form DPs as well, but this is the most commonly used framework. Now, sort of moving on to our specific problem and our specific use case, which is looking at ensembles in RL. I would like to start with looking at ensemble methods, typically in machine learning. So in machine learning, we have a lot, ensemble methods such as bagging and boosting that typically have shown to have really good performance compared to the baseline or individual models. But unlike supervised learning problems, in RL, you more or less require to interact with the environment. Now, however, a case can be made here that, with the recent advancements in batch reinforcement learning, you would essentially try to learn, multiple policies from a fixed, a batch of experience, but that has its own problems relating to exploration and sort of other constraints related to how much of how good a policy that you can learn, and also very highly dependent on the samples that you basically use while learning the policy. So here, for our use case, we typically look at model-free reinforcement learning algorithms. So in deep reinforcement learning, we typically use neural networks to approximate value functions and policies. So a typical life cycle of an RL algorithm basically has a policy, and that particular policy is used in the environment to basically do a rollout and collect samples. Using those collected samples, we try to estimate a value function or try to learn a model. And using that, we try to optimize our policy, and then this basically reiterates again and again. So in this process, there are a few challenges. So the first is you have a lack of robustness and a sensitivity to hyperparameters. Small changes in hyperparameters essentially leads to significant drop or change in performance. And also you have high sample complexity, and which makes it very expensive to train. So if you essentially want to really get a good optimal policy that you want to again deploy in the real world, you need to collect a large number of samples, and that is really expensive to do. So considering these problems and how we would want to do ensembles in RL, we look at this following case, whereby if you want to learn a single model, and if a single model requires n samples from the environment to learn a good policy, and the associated computational cost is C, then if you want to learn an ensemble, which is m models, you would ideally require m times n samples and n times c in computational cost as the upper bound. But what the problem that we're trying to solve, or what we ideally want to do, is can we try to learn m models from only n samples while still only having a computational cost of C. So I would want to go a bit into the prior work related to the use of ensembles in RL to basically set the context of how we are different. So most of the prior work sort of started around 2008, leading to the recent years. So in the early years, you would have a larger focus on classical RL algorithms, and it mainly involved, naive combination of value functions or policies as part of the ensemble. And typically, these were tested on very small state and action spaces, so there wasn't really an emphasis on sample efficiency. But in recent years, you have a number of works such as in average DQN, bootstrap DQN, and sunrise that have typically looked at larger state spaces and larger action spaces and try to solve the same problem while keeping sample efficiency as part of its agenda. So looking at average DQN. So in average DQN, you have multiple Q networks, and the different Q values essentially average together. And the goal here is that by averaging different Q values from multiple networks, we're trying to reduce the overall variance in the estimation, and therefore trying to make the overall algorithm more robust. In bootstrap DQN, you have again similarly multiple Q networks that are trained in parallel, but so instead of combining them, you randomly sample Q networks and basically use that to interface, and that sort of improves the overall performance of the agent. And most recently, we see Sunrise. Again, you have multiple queue networks, but they make a small modification to how the final action is chosen, and that's using the upper conference bound. By looking at the upper conference bound, you're able to also allow for exploration while the agent is acting in the environment. So these kind of summarizes like the major prior work in using ensembles for reinforcement learning. And as you can see, the commonalities here, most of them do off-policy RL and are very kind of reliant on learning a queue function. And so they're very restricted to what sort of algorithm you can apply them to. So the idea here is also that you would want to develop a framework that can scale whether it's off-policy or on-policy. So again, reiterating, so our goal is we want to learn a diverse set of models and from n samples with the computational costs.
I think we lost Rohan. Just wait for a couple, for maybe half a minute or two. We are just trying to reach Rohan. Just give us a minute. Rohan is reconnecting, so we'll just give him a minute. Sorry about that.
Yeah, sorry, yeah, I'll just reconnect. Sorry for that.
So you can share your screen. Yes, Rohan, we can see your screen. Rohan, we can't hear you though.
Hello, can you hear me?
Yes, we can hear you.
Okay, sorry about that. Yeah, maybe I'll just start at this slide. So, yeah, as I was mentioning here, so our learning policies framework is sort of inspired by these three basic points that I've come across in theoretical deep learning. So the first one is the learning rate annealing generalizes better than using a small constant learning rate. High initial learning rate basically influences the local minima to which the model will converge. And the final performance of a model is correlated with the local optima to which the model converges. So using these ideas, the goal is we want to learn a diverse set of policies by leveraging the performance at these multiple different local minimas. So what you see on the left here is you have a vanilla-like use case whereby in the loss topology, you are starting at some point, and then you have a fixed constant learning rate or an annealing learning rate schedule, and you basically converge at some local minima. And on the right is what essentially you would like to do, which is you start at some point in the loss topology, and you ideally want to leverage the performance at these multiple different local minimas. So the way that we do that is we use a cyclical learning rate schedule where the model is perturbed at regular intervals and is forced in and out of these different local minimas. So the formulation for this learning rate schedule is as follows, where it's the two main hyperparameters which it's dependent on is basically alpha 0, which is the initial learning rate, and then capital M, which is the total number of models. So as you can see on the figure below, as we have basically started a high initial learning rate and we anneal the learning rate to a small value, when the learning rate reaches a small value, we assume that the model has converged to local optima, and we save the parameters of the policy at that point, and we treat that as our first policy. Then we bump up the learning rate and do this multiple number of times in order to obtain our different sets of policies. So this is the kind of way that we sort of obtain our number of policies that we need to use finally for the ensemble. Now, as you can imagine, there is a caveat here, which is you might be obtaining a large number of models, but there could be a poor set of policies within that larger set of capital M policies that we obtained. So the idea here is that we would want to select a smaller subset in order to avoid bias from the inferior policies. And the idea, and this is where it gets tricky. So in order to select the best policies, you would want to select the ones which have good performance but are also diverse. So the reason diversity comes into the picture is if you have a set of policies or a set of models that are not at all diverse, then essentially all of them would behave the same and they're not really getting any sort of benefit from an ensemble. And if you have a set of models or policies that are extremely diverse, they would not have any sort of overlap and they would not agree on a particular final a prediction, and that would not really also contribute much to the ensemble. So the idea is that you want a set of policies that have an adequate amount of overlap between them so that they can act well in an ensemble. So in order to do that, we have the policy selection framework, which is a constraint optimization framework that uses the trajectories that we obtain during training to basically select a subset of policies. So this constraint optimization framework has two parts. One is a model error term and the second is the KL divergence term. And the model loss term optimizes for the performance while the KL divergence term optimizes for the diversity. Going into more detail, so the objective here is to basically minimize the following term. So you essentially have this objective function where P of S is the probability of observing a particular state, Wi is the Lagrange multiplier for each policy that you have, and Bi is essentially the combined loss of your model error term as well as the KL divergence term. And the constraints here are basically set on your Lagrange multiplier such that the sum of your Lagrange multipliers across all the models should be equal to 1, and each of them should be greater than or equal to 0. I'll go into more detail as to how the calculation of the model error term is basically done. But here you essentially have a hyperparameter beta that balances between the model error term as well as the divergence term. So in order to calculate the model loss term, we make a critical assumption here, which is that the action that's taken by ensemble of all the policies that we obtain is kind of like the optimal action. And what we do here is we basically take the action taken by each of the individual models, we compare that with the optimal action and see if the error that the agent has or the particular model has seen at that particular state action pair is greater than the threshold. If it is greater than the threshold, then we basically augment the loss term by an additional value of 1, otherwise 0. And we basically present these two cases to account for both continuous and discrete action spaces. And by doing this, we essentially calculate the loss term across all the different policies that we have. And by minimizing this objective function that we've seen before, we obtain the values of the Lagrange multipliers. And in order to choose the best subset, we essentially rank the value. We essentially rank these Lagrange multipliers and basically select the top m values. So in order to sort of check the efficacy of a framework and sort of evaluate it well, we basically consider two major simulators. So the first one is a raw visual simulator known as Atari, and the other is a vector-based environment or a simulator known as Muzoko for the robotic domain. And we conduct our experiments on standard deep reinforcement learning algorithms such as A2C, DDPG, PPO, TRP, and SAC. The reason that we do this is basically to show that our framework is not restricted to any particular algorithm, such as on policy or off policy. It can work across any of them. And we also established two naive baselines. So these are naive baselines that people would maybe start with if you're just considering ensemble. And ideally, we would want to outperform these baselines. Otherwise, it's sort of meaningless to have any sort of framework. So the two baselines that we have here is, you have M models of the same algorithm that's basically trained independently and then used as an ensemble. And the other case is you have M models that are trained on different algorithms and then basically used as an ensemble. The reason we consider these two baselines is essentially to sort of match what we do in classical machine learning, whereby we do, we essentially have multiple algorithms and we do things like voting and so in order to mimic the same kind of thing in the RL space is why we have these two baselines. But this is not enough because these are very naive baselines. What we'd also want to compare is against some of the state-of-the-art reinforcement learning algorithms. So some of them are Rainbow DQ and Simple and Sunrise. And these algorithms are particularly emphasize on sample efficiency, and we want to also see how sample efficient our framework is. And so we also compare against these algorithms. So we'll basically start with the results on the learning policy side. So during the training phase, we're essentially just using the cyclical learning rate schedule, and we're basically learning multiple sets of policies. So here what you see on both the plots is an algorithm A2C, which is the blue one, which is the vanilla version of it, and the red is essentially Searle that basically uses A2C with the cyclical learning rate schedule and basically saving the model parameters at the respective points. And this is the same case with Half-Sheeter here, which is a Muzoko domain using the algorithm SAC. And we see that even while just the training phase, we see that Searle is able to sort of outperform, like the policies for Searle seems to outperform like the baselines. What we do here is we essentially want to compare the diversity among the policies that we obtain using Searle. So on the extreme left, on the extreme right, what you see is the KL divergence between the action distributions of the policy that we obtain on the two baselines, and in the middle we have the same for Searle. So when I say action distribution, what we do here is we have a set of fixed states and we evaluate the policies on these fixed states, and we basically obtain the distribution of action for each policies. We see how much overlap there is between these different policies. And again, as I mentioned earlier, this kind of proves our point that extreme diversity is harmful and that very low diversity is also harmful. In the case with Searle, you see that you have some sort of adequate amount of diversity between the policies, while for the two other baselines, they're extremely diverse. And that's why they don't really perform well. And I'll go to the results to show the same. So we also want to look at what is the ideal performance or what is the performance of the policy that they've learned from scratch. So through the learning policies framework. So here we have 5 policies that we have learned, and we look at their individual performance during the evaluation phase as to how well do they perform. And we see that out of the 5 policies, more or less 4 of them perform equally well, while you have one particular policy that really doesn't match that performance. And you see the ensemble of all the 5 as part of this particular bar plot, and you see that they tend to sort of outperform all of the existing individual policies. And this goes to show the power of having a diverse set of models. This particular plot also emphasizes the need to have a policy selection framework, because you can see that out of all the 5 policies, you have one particular policy that kind of performs suboptimally. So ideally, when you want to do an ensemble, you would want to filter this out or prune this policy out and basically use the remaining 4 or a smaller subset as per your choice. So going along the similar lines, we want to look at the policy selection framework and consider a simple example of doing that. So say that we want to select 3 out of the 5 policies that we have essentially learned here. So there are totally 10 different ways you can do that. And here you essentially see similarly the action distributions between the policies. And what essentially we see here is that there is at least one or more optimal subset that we can choose from the total 5 for using our ensemble. And when we measure the performance of all these different 10 subsets, what we see is that there is one particular subset that has maximum performance, while there are other subsets that are not really good. And this goes on to show our hypothesis that we need to prune out and select a subset of policies. And finally, we would like to compare with some of the baselines. So these are the naive baselines that we introduced earlier, which is B1 and B2. And we compare against Searle as well as the state-of-the-art algorithm versus when we use A2C as the base learner for Searle. And we see that for both these environments, we're able to get like a performance that beats state-of-the-art. We also look at a larger number of environments in the Atari game suite. So we compare across around 15 environments in Atari game suite, and we see that for a majority of the environments, we beat the state-of-the-art. As I mentioned earlier, Rainbow, DQ, and Simple, Curl, and Sunrise are algorithms that emphasize ensample efficiency. So even though they have only been trained on 100,000 interactions, we see that Searle is able to beat the baseline. Searle is able to beat the state-of-the-art algorithms even at such a small number of interactions. So typically the interactions are in millions. So typically they are in like 20 millions or 30 millions. But even at such a small number of interactions, Searle is able to beat the state-of-the-art algorithms in terms of performance. Similarly, for the other environment, which is Mujoko, we see that for across the 6 environments, we outperform the baseline. We outperform the state-of-the-art in 5 of them. Finally, I just want to emphasize a bit on the ablation studies that we did, because there are no free lunches. So we are not trying to say that Searle is the most clean framework. There are essentially two different hyperparameters that would have to be looked at, and that essentially controls the performance of Searle, which is essentially the number of models that you want to learn, and essentially the initial learning rate that you set. So what we've typically seen from our ablation studies is that if you typically choose between 3 to 7 models for your performance, as part of learning your policies, it typically performs well across most environments and across most algorithms. And as part of the learning rate, there is no hard and fast rule to select an optimal value learning rate, as you might well be aware. So typically, if you're using any baseline algorithm, any baseline deep reinforcement learning algorithm, and you're using a certain learning rate, typically if you scale the learning rate by 2 or 3 times and basically use that as the initial learning rate, you typically be able to get really good performance. So that's the kind of hand wavy rule that we established for sort of, testing out Searle and sort of implementing Searle. And to basically conclude, I would like to sort of reiterate the point that Searle is very robust, scalable, and it works across any deep reinforcement learning algorithm. So it's not restricted to off-policy settings or on-policy settings or any specific case, as long as it's being optimized using some sort of, deep learning framework. You can typically use Searle on top of the deep reinforcement learning algorithm. And our main contributions in this paper is basically the policy learning framework that essentially allows you to train multiple policies from a single training run, and that's also computationally efficient. Secondly, the policy selection framework that selects a subset of policies that are diverse and perform well in an ensemble. That's it from my side. Thank you for listening, and I can take any questions now.
Thanks, Robin. First of all, thank you for the talk introduction and very interesting. So, if there are any, we have time for questions. If there are any questions, please raise your hand and I'll allow you. Okay, so if there is a question, please do type it in the Q&A box, and I request you to put it in the box if you have any questions. Thanks, Rohan.
Thank you.
Okay, so we'll move on to the final talk of the evening. So this talk is going to be by Harsha Kokel, who's a PhD student at the University of Texas at Dallas. And the talk is about integrating relational planning and RL for effective abstraction. And this was presented at ICAPS 2021. Over to you, Harsha.
Thank you. Do you see my slides?
Yes.
Can you hear me okay?
Yes, great.
Okay, great. Hi, everyone. My name is Harsha. I'm a PhD student at University of Texas at Dallas. And as Arun mentioned, I'm presenting the REPARIAL paper, which is integrating relational planning and reinforcement learning for effective abstraction. This is joint work with my advisor, Professor Natarajan, Professor Ravindran and Arjun from IIT Madras, and Professor Tadipalli from Oregon State. So before getting to our paper, I wanted to motivate why we are integrating reinforcement learning and planning, right? So we have seen that reinforcement learning has been successful in very complex games, and it has been very adaptive and robust to uncertainties, but it still relies on a huge amount of data and is not effective for long horizon problems. We all know about the sparse reward problem and how hierarchical RL was proposed for that. And it is still limited in generalizing to different tasks. Whereas the planning literature, which is also looking at the same kind of sequential decision-making problems, heavily relies on prior knowledge. It needs a complete definition or description of the domain written in a particular format, but it is better at generalization. It does not require data because it takes in a lot of domain description. It does not require data, but it is not able to handle uncertainties very well, uncertainties and noise very well. So that's why there's a lot of interest in integrating planning and RL. There has been recent papers that have shown that using some form of high-level instruction in form of policy sketches can enable RL agents to learn modular policies, which can be very effective in multitask RL problems. There is work called PlanQ learning, which uses planners, the domain definitions, to shape the reward function and guide the Q learner. There is another work called Perol, which is also kind of using the symbolic planner to guide exploration in RL and trying to reduce the sample, to improve the sample efficiency. And there are numerous work in robotic systems as well, which have used the various planners in form of PDDL or task and motion planning and integrated it with reinforcement learning to kind of optimize their robot in uncertain situations and also learn in continuous state and action spaces. There was a ICAPS 2020 paper which kind of formalized of a setting where the high level, where a planner can be used at a higher level and RL agent can be used at the lower level. So it is kind of like a two, it actually tries to replicate the two systems of human brain, where one system is trying to be rational and try to plan ahead, and the other RL system is actually trying to is more reactive and is is learning while executing as well. So that's why we are integrating reinforcement learning and planning. But we are addressing this relational domain problem. So let me talk about that a little. We address sequential decision-making problems in relational domains that can have varying number of objects or heterogeneous relationship between those objects, like a graph which can have different nodes, changing number of nodes, different types of nodes, or different types of edges, different relationship between those nodes, things like that. A lot of real world problems are inherently relational. Think of iRobot vacuuming a house. It can encounter different objects on different days. Maybe someday there are toys and some days there's a gold earring on the floor, something like that. So it needs to understand properties of those objects, different objects. An agent that is collecting pink ball from a box, the number of balls can change or the color of the balls can change. But if we train an agent to collect pink balls from, say, a set of 10 balls in the box, we expect it to perform equally well when we have, say, 20 balls. Humans are very good at generalizing in such scenario and are able to collect pink balls even when the number of ball increases to 100. We do that by focusing on one ball at a time and checking if it is pink or not. Our decision of picking the current ball does not depend on the color of the adjacent balls. We understand this. So we kind of ignore the color of the adjacent ball or the number of balls in the box. We kind of figure out what are the irrelevant details and ignore that while making the decision for the current task. Even for a complex task like driving, say if I want to drive from IIT Madras to VIT Chennai campus, for planning the route, I would abstract the local geography to something that may look like this map. I would not plan for every vehicle or on the road or every crossroad, every signal. I would rather plan for which highway to take. Maybe I want to go via the Krompet and Tambram route, or I want to take the Medavakam route. So I would abstract the geography out and make my decision or make my plan beforehand. But then when I'm executing the plan or when I'm actually driving to VIT, I would see a totally different representation of the world. It could be something like this here. And in this representation, I focus on the vehicles that are moving around me, but I kind of ignore a lot of things. Like I ignore all the trees on the left-hand side or all the shops on the left-hand side to make my decision on how fast to drive or which direction to turn. I pick and choose what information is relevant to me at that moment, right? I can, if I might be able to ignore the vehicles that are parked on the left when I'm driving. But if I want to park, I would be looking at those vehicles and those trees on my left. So the key point I want to make here is that different objects and different properties of those objects become relevant based on the task that we are performing. And humans can naturally identify the relevant objects and make this different level and different kinds of abstractions for a given task. We are inspired by this ability of humans and we propose a framework where such abstractions are possible. So let me describe our framework. Our framework, REPAREAL, is a hierarchical framework which has three major modules. One is the hierarchical and symbolic planner at the top. As I mentioned, this would act as a rational thinking agent. And then there's an abstraction reasoner. I would get into this a little later. And we have different reinforcement learning agents at the lower level. So the symbolic planner will kind of give us a high level sub goals of a given task. So for example, so we are in a setting where we have this goal directed MDP. So we are given the goal. As an example, consider this taxi domain. It's a grid world which has like 4 colored location, and there are 2 passengers, P1 and P2, and the task is to transport these passengers from their current location to their destination location D1 and D2. So this task is the goal here, the G in the MDP. this task in our framework is decomposed to a sequence of subtasks. So it becomes pick up P1, drop P1, pick up P2, drop P2. This is done by the symbolic planner. Notice that the symbolic planner does not need all the information of the state. It does not need to look at the grid or the taxi location. It can come up with this plan with a very high level domain knowledge from the users, from the expert. And all these sub-goals are then executed by RL agents. In this case, we'll learn 2 RL agents, one for each type of sub-goal, one for pickup and one for drop. So learning this separate RL agents for different tasks allows us to encode a task-specific state representation for the RL agents. For example, the task that is picking up passenger P1 does not need to know drop location of P1 or of drop or anything about P2. So we can encode the state in such a way or abstract the state in such a way that only the information about passenger P1's pickup location is available to this RL agent along with the grid, because the RL agent has to learn the navigation, right? Similarly, drop agent does not need the information about the pickup locations. I'll get to that. So that is where we have this abstraction reasoner here. So our hierarchical planner gives us the compositionality in the domain, and reinforcement learning agent gives the task, like different reinforcement learning agents for different tasks allows us to have task specific state representations. And as we saw that our original MDP is then decomposed into sub-goals, and we define sub-goal RMDP, where we have the same state action function, but state and action space, but we redefine the transition function and the reward function in a way that whenever this goal is achieved, okay. So the original reward function is the R from R, but whenever we achieve the termination condition, whenever this goal is achieved, the RL agent would receive an additional terminal reward. Okay, there's a lag between my right click and when the slide changes. I'll keep that in mind. So we change this transition function, this reward function here, and add terminal reward TR when the state reaches the termination condition, satisfies the termination condition. And also we change the probability function, that the transition function, in a way that when the goal reaches the termination condition, when the state satisfies the termination condition, the reinforcement learning agent would not take any step, and it will stay in that step. But that would trigger end in the trigger the termination of the current sub-goal, and our reparial agent will then transition to the next sub-goal and trigger the next RL agent. So the main contribution that our paper, as I see it, is how we enable this abstraction for each RL agent, right? How do we enable this task-specific state representation? For that, we define dynamic first-order conditional influence statements that would provide us the influence information of the underlying MDP. So first-order conditional influence statements are actually FOSSAI statements, were originally proposed in Natarajan et al. 2008 paper. It is a template which says that if some condition is satisfied, then then X2 literals are only influenced by X1 literals. So X1 and X2 are a set of literals here. We extend the FOSSAI statements to dynamic FOSSAI statements, which encodes the information that when a particular subtask or subgoal is being executed, then the literals in set X2 at time step t plus 1 are only influenced by the literals in set X1 at time step t. So we bring in this notion of time step, and indicate it as a +1 on top of this arrow. That is why we call it dynamic foci. Using this dynamic foci statement, our abstraction reasoner can figure out a abstract state for any given state based on the task that is being performed, which is encoded here. So let me show that with an example. Consider this heterogeneous relational state. It has entities of two colors, green and orange, and it has two types of relationship between those, the solid edge and the dotted edge. Based on the domain knowledge, a human can specify that if we are performing task 1 on, say, node X, then the value of node X in time step t+1 only depends on the value of node X and the value of node Y, such that Y has an incoming solid edge from Y to X. Additionally, a human can also specify that if we are performing task 1, then the reward for this task only depends on the value of X here. So this is kind of telling us what is the influence in the domain in the original MDP. Given this defoci statement, our abstraction reasoner can figure out that if we are performing task 1 on node 2, then only the subgraph 1 with an edge to 2 is important. All the other things are irrelevant and they can be ignored. Hence we can provide just this state as a state to the lower level RL agent. Similarly, if we are performing task 1 on node 3, then only the subgraph 2, 3, and 5 with this edges are important. Notice that 1 also has a solid edge to 2, but that is not included in this subgraph because our value of X here is tied to 3. The X is tied to 3, so we are only looking at the incoming edges to 3, not any other node. But if, say, we had an additional influence information that the Y, any green node is influenced, the value of any green node Y is influenced by the value of Y and the value of Z, such that there's a dotted edge between Y and Z, then in that case, I would also include the node A and node B in this abstract state representation, because there's a dotted edge from 2 to A and from 3 to A. Again, here C has a dotted edge from C to 5, but we are looking for a dotted edge from green to orange. So this part is not included in the subgraph. In our paper, we show that such abstraction, such subgraph selection from the original state is safe. And to understand why it is safe and why do we guarantee the safeness, I would like to briefly cover a notion of model agnostic abstraction. So we adapt the definition of model agnostic abstraction from Lee, Walsh, and Littman paper. It says that an abstraction function phi, which basically maps the ground or the original state to an abstract state, that function phi is model agnostic if the function preserves the transition and the reward distribution in the abstract MDP. So two states S1 and S2 can have the abstract state, that is phi of S1 can be equal to phi of S2 if and only if S1 and S2 have the same reward function for any action A and an abstract state S bar, and the same transition distribution for any A. By any, it means all A and all abstract states. When this condition is satisfied, the optimal value function of the abstract MDP is same as the optimal value function of the lower level or the original MDP. Hence, any model that is optimal for an abstract MDP would also be optimal for the ground MDP. in our paper, we show that if the defoci statements provided by humans are accurate, if they are satisfied by the underlying MDP, then the abstract state that we obtain in this manner are model agnostic abstraction, and hence the abstraction is safe. In the example, I use the colors and the graph nodes, but actually we are using first order language to represent these defoci statements. And hence it also allows us to, kind of pick the feature that is important. Say if this node green had 5 features, then from those 5 features, we can pick which of the feature is important. We can do that because our defoci statements are actually first order statements. So I talked about the planner, the abstraction reasoner, and the reinforcement learning agent at the lower level. So now let me talk about how everything ties up together. So first we get the initial state from the world, and the REPAREL framework will send it to the hierarchical planner, and then it would give us a kind of a sub goal or sequence of sub goals, a action plan for the reinforcement learning agent. And then for every sub goal or every task, we kind of repeat this loop. And this loop is very similar to how a normal reinforcement learning agent would work. It first gets a state from the environment. It applies the abstraction function and provides the abstract state to the reinforcement learner. And the reinforcement learner would, either using exploration or exploitation policy, would provide an action, which is then executed in the world. And then we see the reward and the next state. And this loop keeps repeating. The key point here is that we don't change the update equation anywhere. So the reinforcement we can use any reinforcement learning policy or reinforcement learning architecture at the bottom layer. The only difference is that in a standard RL setting or an end-to-end RL setting, the update function would receive state, action, next state, and reward as the input. Here we change it to abstract state, action, and abstract next state and reward as input. So we only change what the input is to the policy update equation. Rest all things would remain similar. In our experiments, we evaluate 4 different domains. This is office world, this is craft world, this is box world, and this is the taxi world, relational taxi world that I showed. And we compare it against hierarchical reinforcement learning, the options framework, and taskable RL. Taskable RL, as I mentioned, is a recent paper which formalizes this notion of environments where we can use a high-level planner at the top and reinforcement learning at the lower level. So it is kind of saying that the environments where you can decompose the complete task into multiple tasks are defined as taskable reinforcement learning environments. And we evaluate the performance of REPAREL for sample efficiency, transfer across tasks, and generalization across objects. The bottom chart that you're seeing here is comparing REPAREL with TRL and HRL, the taskable RL and hierarchical RL. As you see, the REPAREL agent requires significantly less number of samples than the other two. This is because our state is abstracted. So hierarchical RL is actually learning the high level decomposition as well, because it is learning end to end. It is also learning the hierarchy, right? In the options framework. Taskable RL is not learning the hierarchy. It is similar to us. It also has a planner at the top level. So it is not learning the decomposition. It is also only learning the RL, lower level RL agents like us. But the difference that we see in this in the sample efficiency is purely because of the state abstractions that we use. Because now we have a very small state. Instead of having like 10 nodes in the graph, we now have only 2 or 3 nodes in the graph, right? And to evaluate on the transfer, we first train all the agents on to transport one passenger in the taxi domain and transfer it to transport 2 passengers in the taxi domain. You see the solid line here is reparable agent, which is transferred from the previous task. We see that the transferred reparable did not need even a single example. It is able to achieve zero-shot generalization when we increase the number of passengers. But the other 2 frameworks are still learning. The next domain that we evaluate reparable for is the office world. This is a grid world where we have an office desk and 2 coffee locations and one mail room, and that we have different tasks here. So we evaluate the transfer across tasks in this domain. And we see that when we train reparable agent to deliver mail, we were able to kind of generalize it to deliver coffee better than all the other frameworks. And then finally, the third task was to deliver mail as well as coffee. Craft World is also a multitask environment where we can have multiple tasks. We choose 4 tasks. Here I'm only presenting 2. First one is to get the wood from the wood location and from the tree. This is the tree, and we have to go there and collect the wood. And then we have to also get the iron. Iron is here. So this is the first task. And the second task is make sticks. It basically needs the agent to collect wood from the wood location and then go to the workbench to kind of make sticks. So if the agent has wood and it reaches workbench, it is automatically converted to sticks. So these are the 2 different tasks that we use in Craft World. It was actually proposed in the Andreas Klein paper, and then it has been used for multitask RL setting quite a lot. So we also use this environment. And we see that reparable is sample efficient on the first task, and it also has a better transfer for the second task. And finally, the third task is the domain that we use is the relational box world. Here the agent, the goal of the agent is to collect the white gem. The gray cell here is the agent, and the colored cell here represents the key that the agent possesses. So the blue cell here is the lock. So agent has to first open this lock, and then it can collect the gem. In the this is the first task, and we see reparable was able to perform significantly better than TRL. We were not able to get any results with the HRL, so we omit that here, and we transfer it to a little longer sequence of collecting key first, then opening the lock, and then collecting the gem. And similarly, then we increase the steps further by collecting one lock, collecting the first key, then opening the lock, and then going to the other lock, and then collecting gem. So we increase the length of the task. And we see that the reparable agent is better able to transfer with the increased number of objects in the domain. So finally, I want to say that human level general intelligence, for human level general intelligence, the ability to detect compositional structure and form task specific abstractions is necessary. Our paper is one step in that direction, that it allows humans to define these task specific abstractions. And there has been a lot of recent work this field is very active right now, and I would like to encourage everyone to read about it. Ludovico and others at IJCLR this month in 2021 presented their work where they are learning the high-level planner. They assume that the lower level optimal RL agents are already available, and they use answer set programming tools to learn the high-level planner. Then Liu et al. In their AAAI paper use cost-based planner at the top, and they learn the cost as well as the RL agent by doing R learning. Then Lee et al. Also use the similar framework, and where they kindly automated the task of defining the termination condition for the reinforcement learning agent. How to define that automatically using the planner, so that they focus on that. Then Abdul Hai et al. In their recent work have focused on learning context specific or task specific in our case. It is task specific state representations for the options framework. Then Patra et al. Have proposed operational models which can learn to plan as well as act in a domain simultaneously. And there's a lot of work in robotic navigation which has integrated planning and reinforcement learning together. And this paper particularly recently showed that I forgot about this paper. Anyway, and we are also extending this framework to deep RL setting, which is under preparation. Any questions?
Great, thanks, Harsha, for the talk. If there are any questions from the audience, please raise your hands. I can unmute you. Or if there are questions, please feel free to type in the Q&A box as well. Harsha, if there are any, please do respond. Thank you very much, Harsha, for the talk, and thanks to all the speakers for the great talks, and also congratulations for getting into these top tier venues and publishing there. So we hope to see more such conference publications and more such workshops in the future. So thanks everybody. Have a good night. Thank you.